Hello there, and welcome to Life Beyond Seen, where curiosity slows down a little, the science stays clear, and the strange parts of the world get the quiet attention they deserve. Tonight, we are heading into deep freshwater rather than deep space, which is honestly a nice change for anyone who prefers mysteries without the added pressure of vacuum. Our subject is Lake Michigan, a body of water so familiar to millions of people on shore that it can seem almost ordinary, right up until researchers look beneath it and find something that should not feel ordinary at all. Hidden on the lake floor are dozens of enormous circular holes, found where most people would expect mud, rock, maybe an old wreck, and not a pattern of giant underwater depressions that seem to ask for an explanation the moment you hear about them. Before we settle into that, I would love for you to notice where you are right now. Are you listening late at night, early in the morning, under a blanket, in a chair, or while pretending you are absolutely going to go to bed after this? And where in the world are you hearing this from, while we drift over one of North America's biggest freshwater systems, the only Great Lake located wholly within the United States? If this kind of slow, thoughtful mystery is your sort of thing, then do give the video a like, maybe subscribe, and let this calm little corner find a few more people who enjoy learning about odd discoveries without being shouted at by dramatic music every 7 seconds. There is already enough noise in the world. We do not need a man with a booming voice yelling, "What they found next changed everything," while a fish swims past in total innocence. We can do this properly. We can take our time. Because what makes this story so compelling is not only that scientists found these strange features, but that they found them in a place many people think they already understand. Lake Michigan is large, busy, economically important, heavily travelled, bordered by major cities, and woven into ordinary life for the people who live around it. It is not some remote, unnamed trench hidden from human notice. It is one of the best-known lakes in the world, spanning about 22,300 square miles, and yet it still managed to keep a very large secret on its floor. That alone is worth pausing over for a second. From the shoreline, Lake Michigan can look steady and readable. You see waves, beach grass, harbours, fishing boats, maybe a line of gulls acting like they personally own the place. On a clear day it can feel open and simple, but the lakebed is another matter. Down below, the surface calm means almost nothing. There are ridges, sediment fields, historic wreck sites, changes in depth, buried geology, and wide stretches that very few people will ever see directly. That mismatch between what a place looks like from above and what is actually happening underneath is part of why discoveries like this land so well in the mind. They remind us that familiarity is not the same thing as understanding. A lake can sit beside cities, carry freighters, shape weather, support recreation, and still hold entire landscapes out of view. Researchers working in the Great Lakes have been very direct about this point. Only a small fraction of the lake bottoms have been explored in detail, and even when maps do reveal something unusual, getting close enough to confirm what it is can take time, equipment, money, and a fair amount of stubbornness. So the mystery is not just that the holes exist, it is also that they could sit there for so long without broad public awareness. What makes the story even better is that the discovery did not begin with a team setting out to hunt for giant mysterious holes. It began with mapping work in Wisconsin's Shipwreck Coast National Marine Sanctuary, a protected area of Lake Michigan that preserves 36 historic shipwreck sites, and is also thought to contain many more yet to be found. That detail matters, because it tells you something about how science often works in the real world. People go out to study one thing, and another thing, completely uninvited, appears on the screen and refuses to be ignored. In 2022, researchers were surveying the lakebed inside the sanctuary, a place already known for maritime history, archaeology, and the long memory of cold fresh water. While doing that work, they started seeing strange circles in the sonar data. Not neat little marks that could be dismissed as a glitch, and not obviously human-made structures either, but large circular forms that looked natural and odd at the same time. It was the kind of finding that does not instantly solve itself. It just sits there on the map looking increasingly suspicious, while everyone involved starts thinking, well, that is going to need a closer look. That closer look turned the circles into something much harder to shrug off. Follow-up work with a remotely operated vehicle confirmed that these were real features in the lakebed, not harmless sonar oddities and not wishful thinking from people who had stared at too many screens. Researchers counted roughly 40 depressions in the area they studied. Reports on the survey described them as lying about 14 miles southeast of Sheboygan, Wisconsin, around 450 feet below the surface and stretching in a line toward Port Washington. Their size made the discovery especially striking. Depending on which observation you read, many of the features measured on the order of hundreds of feet across, with common figures landing around 300 to 600 feet across, while some researchers described many of them more broadly in the 500 to 1,000 foot range and about 20 to 40 feet deep. Either way, these are not tiny potholes on the bottom of a lake. They are massive depressions in dark water, large enough that once you picture them properly, the phrase mysterious holes starts to feel almost too casual. It sounds like something you could fix with a shovel in an afternoon. These are not those kind of holes. Naturally, the next question is what they actually are. Right now, the honest answer is that scientists do not know for certain. Some researchers think sinkholes are the most likely explanation, especially because similar underwater depressions in Lake Huron turned out to be sinkholes formed when groundwater dissolved bedrock below and the surface layer collapsed. Lake Michigan sits partly on limestone, and limestone is the sort of rock that can be eaten away by groundwater over time. That makes the sinkhole idea reasonable, and maybe even the leading possibility. But the team looking at these Lake Michigan features has also been careful not to pretend the case is closed. At least one researcher noted that the Lake Michigan structures seem unusually large and strangely circular, compared with the better-known Lake Huron examples. Another possibility raised in reporting is that they may have formed through upwelling water from below or trapped hydrocarbon gas escaping through deep sediment. In other words, scientists have solid leads, but not a final answer. The features may end up in the sinkhole category, or they may teach researchers that this part of the lakebed has its own process going on. At the moment, the mystery is real, and that is part of the appeal. There is another reason people in the research community are paying attention, and it goes beyond the simple fun of finding something weird underwater. In Lake Huron, submerged sinkholes have turned out to be remarkable habitats. They're cold, low in oxygen, rich in sulfur chemistry, and home to microbial communities that do not just survive in those conditions, but actively thrive in them. Scientists studying those systems have described them as useful windows into environments that may resemble parts of early Earth, back when oxygen was scarce and microbial life dominated the planet. NOAA and university researchers have been explicit about that comparison. Some of the Lake Huron sinkholes are treated as time capsule-like settings because they give scientists a chance to study living communities under conditions that echo an older biosphere. That does not mean the Lake Michigan craters already have the same chemistry. It means researchers have a very good reason to investigate whether they might. If groundwater is moving through these depressions and if it carries unusual chemistry with it, then the holes could be more than an interesting geological puzzle. They could be biological laboratories sitting quietly on the lake floor, doing chemistry in the dark while the rest of the lake goes about its business overhead. That possibility changes the mood of the whole story. It is one thing to hear that researchers found large circular depressions underwater. It is another to realise that such places might support rare ecosystems, preserve clues about groundwater movement, and help scientists think about how life functions in low oxygen settings. Researchers who work on Great Lakes sinkholes have connected them not only to early Earth conditions, but also to larger questions about biology in extreme environments. Some have even pointed out that these systems are useful analogues for environments beyond Earth, because they show how life can organise itself around unusual chemistry, rather than the conditions most of us think of as ordinary and friendly. Again, That does not mean Lake Michigan has suddenly become a freshwater version of another planet. It simply means that weird holes in a cold lake can matter for reasons that go far beyond a catchy headline. A depression in the lakebed might tell you something about collapsed limestone, buried groundwater pathways, microbial metabolism, oxygen history, or how much of a supposedly familiar place we still have not properly examined. That is a lot of scientific value packed into what first looked like a set of suspicious circles on a map. And then there is the setting itself, which honestly seems almost designed to make discoveries like this feel extra eerie. The Great Lakes are packed with maritime history. NOAA notes that an estimated 6,000 shipwrecks lie beneath the 5 lakes, including around 1,200 in Lake Michigan alone. The Wisconsin Shipwreck Coast Sanctuary exists because one stretch of this freshwater world preserves an unusually rich collection of wreck sites from the 19th and early 20th centuries. These lakes have carried commerce, migration, industry, storms, military training, fishing and tragedy for generations. Wrecks vanish into them. Some are rediscovered decades or more than a century later. The water is cold enough in many places to preserve remains with unsettling clarity. So when scientists find something new and unexplained on the bottom of Lake Michigan, it lands in a place that already has a long history of hidden things. That does not make the craters supernatural, and it does not turn every sonar anomaly into a ghost story. But it does add a layer of context that is hard to ignore. The Great Lakes are not blank blue spaces on a map. They are crowded archives, and sometimes the archive gives up something nobody expected to read. I think that is one reason this discovery grabs people so quickly. It manages to be scientific and unsettling at the same time, which is a very effective combination. There is no need to exaggerate. Nobody has to invent monsters. The real version is interesting enough. Researchers were looking for shipwrecks, or mapping an area known for them, and instead they found dozens of huge circular depressions in deep water. They sent equipment down and confirmed the shapes were real. They compared them with known sinkholes in another Great Lake. They noticed the possibility of unusual chemistry in ecosystems. They admitted they still do not know exactly how the features formed. That is the whole story structure right there, and it is a good one because it has the right amount of certainty mixed with the right amount of restraint. We know enough to say something remarkable is there. We do not yet know enough to pretend the puzzle is solved. For science, that is often the sweet spot. For the rest of us, especially at the end of the day, it is the kind of mystery that sits well in the mind because it feels grounded. Strange, yes. Wildly speculative, no. Just strange enough to keep us listening. So as you settle in a little further, picture the scene as plainly as you can. Above, an enormous freshwater lake that many people know by beach days, harbours, city skylines, and weather reports. Below, deep water, low light, old geology, old wrecks, and a patch of lakebed where sonar started drawing circles that did not belong in anyone's ordinary mental picture of Lake Michigan. Not little circles, not maybe circles, large ones, dozens of them, waiting in cold water until somebody passed overhead with the right tools and the patience to pay attention. That is where tonight's story really begins. Not with a legend, not with a rumour, and not with a diver shining a flashlight into the dark and gasping on cue for the camera. It begins with methodical mapping, a protected shipwreck coast, a set of screens aboard a research vessel, and a moment when the lake quietly revealed that its floor was not quite what people thought. From there, the questions multiplied very quickly, and the first of them is the simplest one of all. What exactly did the researchers see when those strange circles first appeared on the map? What makes this story so effective is that the discovery did not begin with anyone chasing a dramatic mystery. Nobody set out with a clipboard labelled Giant Unknown Holes. Nobody left the harbour saying, "Today we shall uncover something deeply unsettling and hard to explain." The actual beginning was much more ordinary, which is often how the best scientific surprises happen. Researchers were doing careful mapping work inside Wisconsin Shipwreck Coast National Marine Sanctuary, a protected stretch of Lake Michigan established in 2021, and covering about 962 square miles along Wisconsin's shoreline. The sanctuary is known for its maritime history and protects 36 known historic shipwrecks, with historical research suggesting many more may still be there, waiting for the right equipment and the right patience. That setting matters because it explains why anyone was scanning this part of the lakebed in the first place. The sanctuary is not just a scenic patch of water with a nice name. It is an active research area, part archaeology, part exploration, part preservation project. Lake Michigan's cold fresh water has helped preserve wrecks in unusually good condition, which means the lake floor in this region is not just geology. It's also a record of trade, storms, mistakes, navigation, industry, and the occasional very bad day at sea. So when researchers moved through these waters with sonar, they were doing the sensible thing. They were trying to understand the bottom better, document what was there, and improve the map in a place where the past has a habit of sitting quietly in the dark for a very long time. That is where the story takes its turn. In 2022, during a mission to map the lakebed inside the sanctuary, sonar imagery revealed shapes that did not fit neatly into the team's expectations. The reports that followed described them as strange circles on the bottom of Lake Michigan. At first, they were not yet confirmed holes in the lakebed, just unusual circular features appearing in the data. That distinction is important, because sonar gives you a picture that still has to be interpreted. It can show outlines, shadows, textures, changes in elevation, and suspicious forms, but it does not lean over your shoulder and explain itself. It simply presents the evidence and leaves the humans to start muttering. In this case, the muttering seems to have been immediate. The circles looked odd enough that they stood out at once, yet natural enough that they did not look like obvious wrecks or debris fields. They were just there, clean and circular, as if the lakebed had been pressed down from above by something enormous and very tidy. One of the details I like most is that the people involved did not instantly oversell what they were seeing. They did not slap a final explanation on it and declare victory. They looked at the sonar and recognised that the features were unusual, but they also understood that unusual is not the same thing as understood. This is one of the more respectable habits in science, though admittedly less exciting to those who want every mystery solved before the end of a commercial break. The shapes looked like depressions or holes, but until someone got close enough to confirm them visually, the discovery sat in that interesting middle ground between suggestion and proof. That middle ground can last a while. A lakebed map might show you something compelling, but turning a compelling shape into a documented feature requires more work, more funding, more ship time, and a willingness to go back out and look again. The fact that the circles were found in a place already associated with shipwreck hunting added another layer to the moment. Similar sinkhole-like discoveries in Lake Huron had also first come to attention during acoustic surveys aimed at finding historic wrecks. In other words, the Great Lakes have developed a slight habit of hiding geological puzzles in the margins of archaeological work. You go looking for a schooner and the lake quietly offers you a much older problem. That seems almost unfair, but in a productive way. According to UWM's reporting, Steve Ruberg of NOAA's Great Lakes Environmental Research Laboratory pointed out that the Lake Michigan features were discovered accidentally, in a manner very much like the earlier finds in Lake Huron. That parallel immediately made the new circles more intriguing, because it suggested they might belong to a broader pattern of submerged geological features in the Great Lakes, even if their exact nature was still unresolved. There is something very human about that first stage of discovery. A screen lights up with shapes nobody expected. The shapes repeat. They are clearly not random static. They are large enough to matter. They do not match the usual mental template of what the bottom in that area is supposed to look like. The team cannot yet say precisely what they are, but they also cannot ignore them. At that point the project changes, at least a little. A mapping mission stops being only a mapping mission. It becomes the start of a new investigation. The lake has introduced a side plot and nobody on board gets to pretend they did not notice. It also helps to picture the scale properly, because the word circle can accidentally make these things sound neat and manageable, like the sort of marks a child might draw with a cup on paper. The actual features are much larger. Later follow-up reporting described roughly 40 depressions on the lakebed, many in the range of about 300 to 600 feet across. Some accounts widen that rough size range further, but all of them agree on the basic point. These are giant features, not modest little dimples in the sediment. They sit about 450 feet below the surface and roughly 14 miles southeast of Sheboygan, Wisconsin, laid out in a line extending south toward Port Washington. Once you absorb those numbers, the discovery starts to feel different. These are not lakebed curiosities you would miss unless you blinked. They are enormous forms, and the real surprise is not that they are impressive, but that nobody had clearly documented them before. That last point says as much about the lake as it does about the holes. Even in a major heavily used body of water like Lake Michigan, large parts of the floor are still not mapped in the kind of detail that would make every depression, ridge, and anomaly obvious to the public. The Great Lakes feel familiar from the shore, yet their bottoms remain partly hidden, partly underexplored, and often known best through specialized surveys rather than everyday awareness. This is not because people are lazy or bad at looking. It is because lakes of that size are enormous, conditions can be difficult, and high-resolution mapping takes time. The discovery of the circles is a reminder that a place can be economically central, culturally familiar, and scientifically incomplete all at once. Lake Michigan is not a mystery lake in the sense of being remote. It is a mystery lake in the more interesting sense of being common and still not fully known. Another useful detail comes from the way different observers described what the sonar first showed them. Reports quoting researchers referred to perfect little circles, which is a strangely charming phrase for things hundreds of feet wide. It captures the way they looked in the data, not their actual modesty. From above, through sonar, the features appeared crisp and distinct. That matters because natural formations do not always advertise themselves so neatly. Erosion can look messy. Wrecked debris can look broken and irregular. Sediment changes can blur into long textures rather than clear shapes. These circles did something else. They presented themselves in a way that was clean enough to prompt immediate curiosity. They looked more like real structures than noise, more like depressions than decoration. Enough to be memorable. Enough that once seen, they were not going to be forgotten. Around the same time, shipwreck hunters Brendan Baylod and Dusty Cliffman also noticed the craters, which adds an important human detail to the story. It was not only laboratory staff or federal researchers who saw something odd. People with long experience reading the underwater history of the Great Lakes also recognized that the shapes were unusual. That overlap matters because it suggests the features were striking across different communities of expertise. Archaeologists, shipwreck hunters, marine researchers and mapping teams were all, in one way or another, being drawn toward the same patch of lakebed and the same unresolved forms. When that happens, a finding tends to gain momentum. Not because everyone suddenly agrees on what it means, but because enough informed people agree that it needs explaining. The next major step came in late August 2024, when researchers returned for a closer look using a remotely operated vehicle. That was the moment the story moved from sonar interpretation to direct visual confirmation. An ROV is the kind of tool that brings a mystery down from the screen and into physical view. It carries cameras and instruments into deep water, lets researchers inspect features without diving themselves, and gives the public the part of science they tend to enjoy most, which is actual footage of the strange thing rather than a polite explanation that the strange thing may or may not be there. In this case, the ROV survey showed that the circles were indeed depressions in the lakebed. The lumpy bottom inside them could be photographed. Small life forms could be seen on the sediment. The shapes were real. The mystery had survived contact with the camera. That is a good moment in any investigation. It does not solve the problem, but it narrows the argument. Before the ROV visit, someone skeptical could still imagine a mapping artifact or a misread pattern in the data. Afterward, that option becomes much weaker. The team now knew they were looking at genuine holes or craters in the bottom of the lake. It is one of those scientific moments that is both satisfying and slightly annoying, because one question gets answered and several more immediately take its place. Yes, the circles are real, fine. Then what made them? Why are there around 40 of them in that area? Why are they arranged the way they are? Why do they appear so circular? And why were they sitting there so quietly beneath a very famous lake while most people above had no idea at all? At that stage, the sinkhole idea naturally moved to the front of the conversation. Researchers had a nearby example to compare with, because similar depressions in Lake Huron had already been investigated and identified as sinkholes formed when groundwater dissolved limestone bedrock from below until the surface collapsed. Lake Michigan partly sits on limestone too, so the hypothesis made geological sense. If limestone is present and groundwater has pathways through it, then dissolution and collapse are plausible. That is the sensible version of the story, and it may yet prove correct. But what makes the discovery section especially interesting is that the scientists involved did not simply declare, "Mystery solved, they are sinkholes, everyone go home." Steve Ruberg specifically cautioned against assuming they were just like the Lake Huron examples. He noted that the Lake Michigan features are much bigger and strangely circular. That caution is valuable. Similar does not mean identical. A leading explanation is not the same as a complete explanation. This restraint also makes the discovery itself feel more credible. When experts say they do not know yet, and then explain why they do not know yet, it tends to increase confidence rather than weaken it. Here, the unknowns are concrete. The features resemble sinkholes, but they are unusually large. The bedrock context supports one mechanism, but shape and scale leave room for other processes. Some reporting also raised possibilities like upwelling groundwater or trapped hydrocarbon gas influencing the formation of the craters. Those ideas are not final answers either, but they show the investigation is open rather than frozen. The discovery phase is doing what discovery phases should do. It is collecting evidence, comparing analogues, and resisting the urge to turn a fresh observation into a finished story. There is also a practical side to why this part of the story matters. Finding the holes is not only dramatic in a visual sense, it changes the research map. Once features like these are confirmed, they become targets for future sampling, future camera work, future chemistry measurements, and future geological analysis. A survey that might otherwise have focused mainly on cultural resources now has a set of geological coordinates that deserve repeat visits. That can influence where vessels go, where instruments are lowered, and what kinds of partnerships develop between archaeologists, ecologists, geologists, and limnologists. A discovery on the lake floor is never just a discovery on the lake floor, it reshapes the agenda above it. Suddenly different specialists are interested in the same place for different reasons, which is often when the most useful science starts happening, and the timing adds its own texture. The sanctuary itself only took effect in August 2021. The strange circles were first spotted in 2022. A closer ROV look followed in 2024. That means the discovery sits inside a very recent timeline. This is not one of those stories where a Victorian naturalist scribbled a vague note in a field journal and everyone argued about it for 140 years. This is a modern finding, made with modern mapping tools in a newly designated sanctuary, and still early in its scientific life. We're not hearing the final settled lecture. We're hearing the beginning of an investigation while the evidence is still fresh, and the main explanations are still being tested. For a script like this, that is ideal. The mystery is not worn smooth yet. It still has edges. There is another thing the discovery does very effectively, and that is shift your mental picture of Lake Michigan. Before you hear this story, you may think of beaches, cold wind, harbours, ferries, city skylines, fishing, storms, or maybe one particularly unpleasant childhood experience with wet socks and sand. After you hear it, the lake acquires depth in a different way. Not just physical depth, but investigative depth. The floor becomes active in the imagination. You start to picture sonar passes crossing black water. You picture the data returning to the vessel in bands and shapes. You picture someone noticing circles where there should not be circles, then calling someone else over to look. You picture the slow process by which a shape on a screen becomes a reason to launch another expedition. That is the real discovery. Not just the existence of the holes, but the moment the lake stopped being background and started behaving like a problem. It is worth lingering there a little longer, because this is where the tone of the whole topic gets set. The holes were not found through myth, rumour, or a dramatic eyewitness account from a lone fisherman who definitely saw something huge and would rather not discuss it. They were found the unglamorous way, by mapping, by grids, data, repeat passes, and the discipline of looking closely at a place other people assume they already know. That is one reason the mystery works so well. It is anchored in method. The lake did not suddenly become strange because somebody told a spooky story about it. It became strange because researchers did their job carefully, and the bottom did not match expectations. That kind of strangeness is harder to dismiss, and, in its own quiet way, more unsettling. So when people say scientists found mysterious holes in Lake Michigan, the discovery part of that sentence carries more weight than it first appears to. It means a newly protected shipwreck sanctuary was being mapped in detail. It means sonar in 2022 revealed repeated circular anomalies. It means those anomalies were compelling enough to bring researchers back. It means a remotely operated vehicle confirmed roughly 40 real depressions about 450 feet down and roughly 14 miles southeast of Sheboygan. It means those features are large, lined up, and still not fully explained. And it means a very familiar Great Lake has just reminded everyone that the floor under its cold water can still surprise the people who study it most closely. Once that much is established, the next step becomes unavoidable. You have the setting, you have the survey, you have the circles on the screen, the return trip, the camera confirmation, and the basic location of the features. What you do not yet have is a proper feel for what those circles are actually like as physical forms on the bottom, how many there seem to be, how regular they look, and why their shape caught so much attention so quickly. That is where the story naturally moves next, because after the discovery comes the stranger part still. Dozens of almost unnervingly tidy circles sitting in deep water, waiting to be measured one by one. Once those first passes across the sanctuary had revealed the anomalies, the mood of the whole investigation changed. The discovery itself was already enough to get attention, but what truly fixed these features in people's minds was their shape. They were not random gouges, not broken strips of sediment, and not the chaotic scatter you might expect from wreck debris or rough lakebed erosion. They presented themselves as circles, and not vague circles either. In the sonar they appeared with a kind of unnerving neatness, repeated enough times that the pattern could not be dismissed as coincidence. Researchers working in Wisconsin Shipwreck Coast National and Marine Sanctuary had been mapping a region known for shipwrecks, but what emerged from the data was something more geometric and more difficult to mentally file away. Dozens of giant circular depressions on the floor of Lake Michigan, roughly 14 miles southeast of Sheboygan, and about 450 feet below the surface. Later reporting put the count at around 40 features, generally arranged in a line toward Port Washington. That combination of number, depth, and shape is what gives the scene its force. One strange hole would be interesting. Two might look like a local oddity. Around 40, sitting in deep water and echoing each other closely enough to be recognized as a group, feels like a submerged landscape with its own logic. The features are not only many, they are large. Smithsonian's reporting, based on the follow-up expedition, described the depressions as roughly 300 to 600 feet across, while WUWM reported that most of them are about as long as an Olympic swimming pool. Even the more compact end of those ranges is enormous when you imagine it on the bottom of a cold, dark lake. These are not the sort of features a diver casually notices on a weekend outing. They are broad forms in a deep, low-light environment, large enough that once an ROV gets inside one, the edges are no longer a small detail. The crater becomes the surrounding space. The visual quality of the circles seems to have surprised even people who work professionally with underwater data. One report preserved Steve Ruberg's description of them as perfect little circles, which is a wonderfully understated thing to say about depressions hundreds of feet wide. The phrase works because it captures the contradiction. On a sonar screen, the circles could look oddly tidy, almost modest, even though their actual scale is anything but modest. That happens a lot with remote data. A mountain becomes a contour, a shipwreck becomes a silhouette, a huge lakebed depression becomes a clean ring on a display, as if the lake was sketching with more confidence than anyone expected. The result is a strange mismatch between image and reality. What first arrives as a simple form on a screen turns out to be a very large physical feature in deep water, cold enough and dark enough that human intuition does not handle it especially well. It helps to slow down and picture the setting properly, rather than letting the mind flatten it into a nice little graphic. This is Lake Michigan, one of the 5 Great Lakes, a place most people associate with beaches, shipping lanes, skyline views, marinas, ferries, storms, and the ordinary practical business of living near a major body of water. Yet down at roughly 450 feet, none of that shoreline familiarity matters much. Light is limited, pressure is greater, temperature is low. The lakebed becomes a separate environment, one reached through instruments rather than eyes. Noah Ocean. Exploration notes that the Great Lakes collectively contain an estimated 6,000 shipwrecks, including about 1,200 in Lake Michigan alone, and the Wisconsin Sanctuary exists precisely because this region preserves historic remains so well in cold fresh water. In that context, the circles sit inside a bottomscape, already known for hidden things, though not usually for repeated giant circular depressions. The repetition of the pattern is part of what makes the circles so memorable. Humans are very good at noticing recurring forms, especially when those forms seem cleaner than the surrounding world. A single cavity could be interpreted in half a dozen ways. A whole set of them begins to suggest a process, even before anyone knows what that process is. That is why the line of the depressions matters. They are not sprinkled everywhere in a casual, indifferent way. Reports describe them as roughly laid out in a line, which immediately makes the mind start searching for structure. A line suggests direction. Direction suggests history. Something may have followed a weakness in the bedrock, a buried geological boundary, a groundwater path, or some other organising condition that has not yet been fully identified. The circles are mysterious partly because they are circular, but also because they do not appear lonely. They look related. That sense of relatedness is where the darkness of the setting really starts to matter. On land, if someone told you there were 40 large circular depressions arranged in a rough line, you could drive out, stand at the edge of one, compare them, walk the spacing, maybe even talk yourself into feeling normal about it by lunchtime. At the bottom of Lake Michigan, the same pattern becomes more difficult to domesticate. You only know it through sonar sweeps, coordinates, camera footage, and the narrow cone of visibility given by an underwater vehicle. The forms do not announce themselves to passing human bodies. They exist in a place where scale has to be inferred from measurements and images, which makes them feel in a very literal sense remote. There is a difference between seeing a feature and reconstructing it mentally from evidence. The circles live in that second mode. They are known, but they are not familiar. The ROV footage made that remoteness easier to bridge, but only partly. According to Live Science, researchers used a remotely operated vehicle to photograph the lakebed inside one of the holes, and the result showed a lumpy bottom with small critters scattered across it. That detail is useful because it grounds the circles in matter rather than myth. They are not smooth cartoon craters. They are actual depressions filled with lakebed texture, sediment irregularities, and living organisms going about their business with no apparent concern for human suspense. This is one of the quieter pleasures of underwater research. Even the most dramatic discoveries tend to contain at least one reminder that life has already moved in and normalised the place long before scientists arrive with cameras. The crater may feel uncanny to us, but to the animals and microbes down there it is just terrain. That image of a lumpy interior also matters because it pushes back against the idea that the circles are too perfect in some artificial sense. They are circular as large-scale forms, not polished bowls made by a machine. Their outlines appear striking in sonar and in the mapping data, but their interiors still belong to the normal roughness of a lake floor. That distinction lets the mystery stay scientific. If the shapes had looked metallic or constructed, the conversation would have spun off into less useful directions almost immediately. Instead, what researchers seem to have found is something more interesting. Features that are clearly natural looking up close and still oddly regular looking at scale. It's exactly the kind of combination that forces geology to step forward and explain itself. Another reason the circles feel so vivid is that they were found in a place already dense with stories. Around the same time researchers noticed the sonar anomalies, shipwreck hunters, Brendan Baylod and Dusty Cliffman also noticed the craters. That overlap between professional survey work and experienced wreck hunters gives the features extra weight. It means these were not odd marks that only one set of observers was persuaded by. Different people, looking at the underwater world from slightly different missions, found themselves confronted by the same strange geometry. Lake Michigan already trains attention toward the hidden. Wrecks vanish into it. Preserved hulls lie in cold fresh water. Survey lines can reveal remains no one has visited in generations. Into that existing atmosphere, the circles arrived as a second kind of secret, not cultural this time, but geological. The darkness, both literal and narrative, does a lot of work here. These are circles in deep water, which means they were never going to enter public imagination in the same comfortable way as a sinkhole on land. Land sinkholes make the news because they interrupt roads, yards, buildings, and confidence. An underwater depression has no such daily drama. It can remain in place for a very long time without demanding attention. That makes the moment of recognition feel delayed, almost overdue. Once you hear there are about 40 of these giant features down there, the mind immediately starts asking how such things could have been sitting in one of America's most familiar lakes with so little notice. The answer is not especially magical. Much of the bottom has simply not been examined in that kind of detail, and deep water mapping remains a specialised effort. Still, the emotional effect is stronger than the explanation. The lake suddenly seems to have been keeping its own counsel. There is also a very specific strangeness in the phrase, weirdly circular, which WWUWM used while reporting Ruberg's caution that the Lake Michigan features are much bigger and very strangely circular compared with the known sinkholes in Lake Huron. That wording gets close to the heart of the matter. Circularity is not rare in nature, but scale plus repetition plus depth gives it a different tone. If the features had been ragged ovals or crescent shapes, researchers might still be interested, but the public probably would not linger over them in the same way. Circles feel intentional even when they are not. They invite interpretation. They also carry a visual stillness that fits the setting. A line of giant tidy depressions in dark water has a kind of quiet force to it. Not loud, not theatrical, just persistent, like a pattern that refuses to blur into the background however long you stare at it. The comparison with Lake Huron reinforces that mood without dissolving it. Researchers previously found similar depressions at the bottom of Lake Huron, and those turned out to be sinkholes linked to groundwater dissolving limestone below the surface until the upper layer collapsed. Lake Michigan partly sits on limestone too, so the comparison is scientifically sensible. But the Lake Michigan circles are not being treated as a simple copy. Ruberg explicitly said he was not ready to say they are the same kind of sinkhole, because these are larger and unusually circular. That is exactly the sort of statement that keeps a mystery healthy. It places the circles in a family of possible explanations, without pretending the family resemblance settles everything. For narration, that matters, because it lets the features keep their particular character. They are not just examples of something already fully known. They may be cousins, but they are not yet identical twins. Once you start imagining the circles as a group rather than individually, they begin to suggest an entire hidden terrain. Not a flat lake floor punctuated by occasional oddities, but a district on the bottom with its own rules. There is something almost architectural about the way repeated depressions can reorganize a mental map. The lakebed stops being blank and becomes inhabited by form. One circle leads to another, one measurement leads to the count of roughly 40. One image of a lumpy interior leads to the recognition that each depression has its own microtopography. The darkness no longer feels empty, it feels occupied by structure. That does not make the bottom crowded in a human sense. It makes it legible in a new way, which is more unsettling and more satisfying at once. The circles also benefit, narratively speaking, from being big enough to resist trivialization. Sometimes science stories lose their force because the scale is hard to hold in the mind. Here the numbers cooperate. 300 to 600 feet across is a useful size range, because even a tired brain can grasp that these are broad formations. WUWM's comparison to Olympic pool length helps further. Once you anchor the scale, the lake floor begins to feel less like a smooth map background, and more like a place where someone could disappear into the wrong topographic assumption very quickly. That does not mean the holes are dangerous in the dramatic thriller sense. It means they are substantial enough to command respect. They are features you measure, circle back to, and return to with better equipment. The fact that the circles first announce themselves through sonar rather than direct sight adds one final layer to their identity. Sonar is a patient technology. It does not dramatize. It accumulates. It sweeps, records, and gradually reveals that the floor below is not what simple imagination would have predicted. In a way, that makes the circles even more fitting subjects for a slow narrative like this one. They did not burst onto the scene. They emerged line by line, pass by pass, out of careful acoustic mapping. They were noticed because someone was willing to look at a place most people will never see and take its shape seriously. The darkness kept them for a long time. The data brought them back. By this point, the picture is much clearer. Deep below Lake Michigan's surface, in a sanctuary better known for shipwrecks, around 40 giant depressions sit in cold water, roughly aligned, distinctly circular, and large enough to feel almost too orderly when first seen in sonar. A camera has been down into them. Their interiors are real, uneven, and inhabited. Their scale has been measured. Their location is no longer hypothetical. What remains unresolved is not whether they exist, but what process made the lake floor look this way in the first place. And that question becomes much easier to approach once the circles stop being just eerie shapes in the dark and start becoming part of a hidden terrain that had to be mapped, line by line, before anyone could even begin to understand it. To get any closer to understanding those circles, the researchers first had to do something much less dramatic than solving a mystery. They had to build a reliable picture of the bottom itself. That is the quiet part people often skip past when they hear about discoveries on a lake floor. Before anyone can explain a crater, a sinkhole, or a strange depression, someone has to map the terrain carefully enough to prove that it is there, measure its depth, compare its shape to the surrounding bottom, and separate a real feature from noise, shadow, or wishful interpretation. In underwater science, that first step is bathymetry, which NOAA describes as the underwater equivalent of topography. It is the process of measuring depth and building a picture of underwater terrain, because the floor of a lake is not flat any more than dry land is flat. It has slopes, rough patches, sediment plains, ridges, and abrupt changes that only become visible once sound data are turned into maps. That sounds straightforward until you remember the scale involved. Lake Michigan is enormous, and the sanctuary where the circles were found is not a tiny cove that can be understood with one afternoon of scanning. Wisconsin shipwreck. Coast National Marine Sanctuary covers 962 square miles and contains 36 known historic shipwreck sites, with research suggesting many more remain to be found. NOAA has also been very clear that the sanctuary serves both cultural and natural science goals. The mapping work in this area is not only about old vessels, it is also about lakebed habitats, substrates, water quality, and the structure of the underwater environment itself. That is why the floor beneath a well-known lake can still count as hidden. People know the shoreline. Scientists are still assembling the landscape below it. There is a larger reason this matters. NOAA's bathymetry program notes that only 15% of the Great Lakes has been mapped at high density so far under the broader Lakebed 2030 effort. That number is one of the most useful facts in the entire story, because it immediately resets expectations. It explains why a major freshwater system can still produce basic surprises. It also explains why mapping is not just background work. It is the main event for long stretches of time. If only a relatively small share of the Great Lakes has been mapped in the kind of detail that makes subtle features stand out clearly, then every survey adds not just refinement, but genuinely new knowledge. That is especially true in places where geological features and human history overlap, because a better map can reveal both a wreck and a hole in the bottom on the same mission. The tools that make this possible are elegant in a practical way. Modern bathymetric mapping relies heavily on sonar, which uses sound to explore underwater where light and direct visibility are limited. NOAA explains that multi-beam sonar sends out many sound beams at once in a fan-shaped pattern, covering the area directly under a vessel and out to each side. By measuring how long the sound takes to travel down to the floor and return, scientists calculate depth. At the same time, multi-beam systems also collect backscatter, which is the strength of the returning echo. That matters because hard and soft surfaces reflect sound differently. Rock, mud, sand, and protruding structures do not all answer sound the same way, so the returning signal can reveal not only shape, but texture and material clues. When those data are processed, the result is not just a list of depths, it becomes a two-dimensional or three-dimensional map of the bottom. A second tool adds a different kind of detail. Side-scan sonar does not measure depth the way multi-beam does, but it is extremely useful for imaging the bottom and detecting objects on it. NOAA describes side-scan as sending signals out to both sides of the survey path, producing light and dark images based on the strength of the returning echoes. Hard protruding objects tend to create stronger signals and acoustic shadows, while softer sediment returns weaker echoes. It is widely used in marine archaeology, habitat work and object detection because it can cover large areas efficiently and create highly readable images of seafloor or lakebed texture. In practical terms, multi-beam helps tell you the shape of the bottom, and side-scan helps tell you what that shape looks like and what might be sitting on it. Used together, they turn a dark, inaccessible floor into something legible enough for scientists to start making decisions. That combination of tools is exactly the sort of approach NOAA and its partners have been using in this region for several years. Before the circular craters became public, the sanctuary and associated NOAA programs were already building mapping capacity in mid-Lake Michigan. The sanctuary's science page notes that between 2016 and 2020, NOAA's National Centers for Coastal Ocean Science, the Office of National Marine Sanctuaries, and the Great Lakes Environmental Research Laboratory began mapping the area to better understand both cultural and natural features. In 2021, NOAA's Office of Coast Survey surveyed about 70 square miles of the sanctuary, and the sanctuary's 2022 field season included sonar mapping at 13 sites, in addition to archaeological assessments and video collection. This means the circles were not found in a blank zone where no one had ever bothered to look. They emerged in a place where multiple layers of mapping were gradually improving the underwater picture year by year. The 2021 expedition is especially helpful for understanding how a hidden landscape becomes visible. NOAA's summary of maritime heritage in America's inland seas explains that an interdisciplinary team used a coordinated set of crewed and autonomous systems in Lakes Michigan and Ontario, including multi-beam and side-scan sonars, magnetometers, cameras, an uncrewed aerial vehicle, autonomous surface vehicles for shallow water, and an autonomous underwater vehicle for deeper water. That is not technological extravagance for its own sake. It reflects a simple reality. One platform rarely does everything well. Large areas require efficient broad mapping. Complex targets require closer inspection. Shallow and deep zones create different operational problems. So the lakebed is not revealed by one magic instrument. It is revealed by layering tools, scales, and passes until the broad picture and the local details begin to agree with each other. That point is easy to miss if you only look at the final map. A finished bathymetric image feels neat. The process that produces it is not neat in the same way. A vessel moves in planned lines. Sensors record constantly. Scientists measure sound speed in the water, because sound does not travel at exactly the same speed under all conditions. Data have to be calibrated, cleaned, processed, and compared. Multiple surveys may overlap. One tool may suggest a feature, and another may test it. NOAA's Habitat Mapping Group states plainly that multiple sensors and survey platforms are required to survey large areas, and that integrating those datasets can be challenging unless everything is calibrated to common standards. So when the circles appeared, they did not float into view as a finished revelation. They emerged from a long workflow built to make underwater terrain consistent enough to interpret. There is also a physical reason that mapping a hidden landscape can change what scientists think the lake even is. From shore, Lake Michigan often reads as one large body of open water. In mapping terms, it is a quilt of different bottom types, depths, and structures. NOAA's remote sensing program notes that maps showing the depth, shape, and texture of seabeds or lakebeds provide the first indicators of the geological types and biological composition of benthic habitats. That means mapping is never only about lines on a chart. A change in texture may suggest a different sediment type. A rise may imply rock or wreckage. A depression may alter oxygen, water movement, or local biology. The map is not just a picture. It is the first pass at the logic of the place. Once a survey reveals repeated circular depressions, the lake is no longer just a transportation corridor or a backdrop to weather. It becomes a landscape with a geological pattern that demands explanation. That is exactly what happened with the circles. Live Science's reporting on the 2024 follow-up makes clear that the holes were first noticed in 2022 during a mission to map the lakebed inside the sanctuary. At that point, the circles were still anomalies in sonar data. What the map had done was not solve the mystery but force it into focus. The floor under the sanctuary no longer looked like a vaguely understood deep basin, with occasional shipwreck targets. It contained a line of repeated circular forms southeast of Sheboygan, and once those forms had appeared in the mapping data, the next step could no longer be avoided. A camera had to go down. The hidden landscape had to become not just mapped terrain, but visually confirmed terrain. That follow-up step reveals another important feature of underwater mapping. Maps do not replace direct observation, but they tell you where direct observation will matter most. NOAA's own multi-beam guidance notes that broad multi-beam surveys are efficient for systematically mapping large regions, but the deeper the water, the lower the resolution can become. For very high-resolution work, mapping systems often need to get closer to the bottom, which is why scientists tow sensors or mount them on remotely operated or autonomous underwater vehicles. That is the bridge between a hidden landscape and a visible one. The first pass is usually broad and acoustic. The next pass narrows in. In the Lake Michigan case, that narrowing produced the ROV images showing the lumpy floor inside one of the depressions. Without the map, the camera would not have known where to look. Without the camera, the map would have remained suggestive rather than decisive. There is something almost procedural about the way mystery gets stripped down in that sequence. First, the lakebed is surveyed. Then the survey shows irregularities. Then those irregularities are checked against known patterns. Then a targeted inspection confirms whether the anomalies are real structures. The map is not there to excite the imagination, though it certainly does that. It is there to keep imagination from running ahead of evidence. In a place like Wisconsin Shipwreck Coast, that discipline is essential because the same mapping systems that reveal geological features also reveal shipwrecks and other cultural resources. NOAA has described the sanctuary as a place where mapping data are used to support resource monitoring, mooring placement, education, charting, and ecosystem understanding. In other words, the map has to serve many masters. It has to be accurate enough for science, management, archaeology, and public safety at the same time. There is a quieter implication here too. The phrase hidden landscape is not just a dramatic label for dark water. It is a literal description of an environment that exists regardless of whether people have resolved it clearly yet. The circles were always there. The shipwrecks were always there. The sediment fields, hard bottoms and habitat changes were always there. What changed was the resolution of our attention. NOAA's bathymetry guidance makes this point in a very direct way when it notes that modern, higher resolution maps increase the opportunity for discovering new seafloor features. That is not because the bottom becomes more interesting once better instruments arrive. It is because the instruments finally give scientists a chance to see the structure that was present all along. The hidden landscape is not created by mapping, it is uncovered by it. That is why the sanctuary keeps drawing repeat work. In 2025, NOAA Ocean Exploration returned with a project focused on deep-water shipwreck sites, using a hybrid autonomous underwater vehicle and remotely operated vehicle equipped with acoustic, imaging, and laser scanning sensors. The immediate goal in that mission was shipwreck documentation, but the expedition description makes a larger point about the region. The sanctuary includes wrecks from 130 to 480 feet deep, and the team's data collection on deep sites was designed not just to capture better images of wrecks, but also to learn more about the lake floor itself. High-resolution point clouds, photomosaics, sonar-based three-dimensional pictures, and detailed site context all help show that the bottom is being read as a landscape, not just as a set of isolated targets. The circles belong to that larger shift in perspective. For the people on a vessel, this kind of work probably feels less mystical than it sounds in a story like this. It is likely a mix of careful planning, instrument checks, screen watching, route adjustments, and the occasional weather-related frustration. NOAA's 2025 expedition page mentions rough weather and technical glitches affecting plans, which is a good reminder that underwater mapping has to negotiate with the lake itself. Lake Michigan is not a laboratory tank. Conditions matter. Sound speed profiles matter. Vessel motion matters. Equipment deployment matters. So when a map finally comes together cleanly enough to reveal a hidden pattern, there is a lot of plain effort behind that moment. The circles in the dark only become circles in the dark because many less glamorous steps have already gone right. Once you think of it that way, the discovery becomes even more satisfying. The hidden landscape was not exposed by accident alone. It was exposed by a sustained mapping culture in and around the sanctuary, years of lakebed characterization, coordinated NOAA work, autonomous platforms, sonar sweeps, targeted surveys, and follow-up visual inspection. That is why a familiar Great Lake can still surprise people who study it. The map is still being built. Every new pass adds relief to a picture that was once too coarse to trust in detail. In this case, what emerged from that growing picture was a line of giant circular depressions, clear enough to confirm and strange enough to resist immediate explanation. Once a map gives you that much shape, the next question becomes more geological than cartographic. You stop asking how the bottom was revealed and start asking what kind of bedrock, pressure, groundwater, or buried history could make so many large circles appear in one place. By the time researchers had confirmed that the circles on the floor of Lake Michigan were real depressions and not just odd sonar signatures, one explanation naturally moved to the front of the line. Not the only explanation, and not a proven one yet, but the one geologists would probably reach for first if they were handed a map, a depth profile, and a body of water sitting over carbonate bedrock. The idea is simple enough to say without making it sound simple in practice. These features may be sinkholes, underwater sinkholes to be precise, formed not by sudden drama visible from a roadside, but by long, patient geological work happening under the lake floor where groundwater, bedrock, chemistry and time have been negotiating for a very long while. That theory has become the leading candidate partly because similar features in Lake Huron turned out to be sinkholes, and partly because the basic ingredients for sinkhole formation already exist in this part of the Great Lakes system. To understand why this theory has real weight behind it, it helps to step back and define what a sinkhole actually is in geological terms, because the popular version usually involves a car, a news helicopter, and a reporter trying to sound calm while standing next to a very regrettable hole. The Michigan Geological Survey gives the cleaner version. Sinkholes are common where the rock below the surface is limestone, other carbonate rocks, salt beds, or similarly soluble materials that groundwater can dissolve. As the rock slowly dissolves, underground spaces and caverns develop. For a while, the ground or sediment above those spaces may remain intact. Then, once there is not enough support left, the overlying material can collapse and leave a depression at the surface. The US Geological Survey places this within karst terrain, which forms when soluble rocks, especially limestone and dolomite, are dissolved and leave behind a hydrogeology shaped by fissures, fractures, conduits, caves, springs, and sinkholes. That word karst is useful here because it sounds technical without being mysterious. It simply refers to a landscape shaped by dissolution. Water moves through soluble rock, widens cracks, enlarges pathways, and gradually turns solid-looking geology into something more like a hidden plumbing system with weak spots. In karst terrains, much of the water does not move slowly and evenly through tiny pores the way people tend to imagine groundwater. Instead, it can travel through networks of fractures and conduits, which means the rock below may be far more hollowed out, irregular, and structurally vulnerable than the surface suggests. In dry land settings, that can produce caves, springs, and sinkholes. Under a lake, the same broad logic can still apply. The only difference is that the final depression ends up beneath water rather than beneath a field or a parking lot, which is probably a relief to the parking lot. That is what makes Lake Michigan a plausible candidate for this kind of process. In the WUWM interview about the discovery, NOAA scientist Steve Ruberg explained that when you look at the geology of the Great Lakes, Lake Michigan and Lake Huron especially sit on a limestone geologic layer laid down roughly 400 to 500 million years ago, with glacial activity on top of that older bedrock. He also said that the Lake Huron features are karst features, where limestone is eroded, a cavern forms, and then that cavern collapses into a sinkhole. In other words, the region already has the right geological background for collapse features of this general type. The bedrock is old, carbonate-rich, and vulnerable to groundwater-driven dissolution. That does not prove the Lake Michigan circles are sinkholes, but it means the theory begins from the actual geology, rather than from wishful guesswork. Lake Huron is the most important comparison, because it gives researchers a nearby example of what submerged sinkholes in the Great Lakes can look like when studied properly. NOAA's Great Lakes Environmental Research Laboratory states that the underwater sinkholes off Alpena in Lake Huron formed when patches of ground beneath the lake collapsed thousands of years ago. The same NOAA material explains that groundwater seeping through the sinkholes has unusual chemistry, including low oxygen, high chloride and sulfate, tied to dissolved limestone underlying the lake. WUWM's reporting on the Lake Michigan discovery summarizes the geological mechanism more directly. In Lake Huron, groundwater eroded the limestone layer on the bottom of the lake, creating caverns, and when the roof of a cavern collapsed, a sinkhole was born. That is an extremely important analogue because it shows the Great Lakes do not merely permit underwater sinkholes in theory. They already contain them in practice. Once that comparison is on the table, the Lake Michigan circles start to look less like a wild anomaly and more like a reasonable variation on an established regional process. The features in Wisconsin, Shipwreck Coast National Marine Sanctuary, are cold, dark, circular depressions on the bottom of a lake that sits on the sort of soluble bedrock associated with karst development. They were discovered in a manner similar to the Lake Huron sinkholes as well, through acoustic surveys being conducted for other reasons. That parallel matters because geology is often easier to trust when it repeats itself nearby. One lake develops submerged collapse features under the right chemical and structural conditions. Another neighbouring lake, sharing important parts of the same deep geological story, shows broad circular depressions in deep water. The sinkhole theory does not feel forced in that setting. It feels like the obvious working model, at least until stronger contrary evidence shows up. Still, this is the part where the script has to stay honest, because the scientists involved have been careful not to oversell the theory. Ruber told WUWM that he was not ready to say the Lake Michigan features are sinkholes, similar to those in Lake Huron. His reason was not vague hesitation. It was based on the features themselves. He described them as much bigger and very strangely circular. That caution matters a great deal. Science becomes much less useful when every resemblance is treated as proof. The Lake Michigan depressions may well be sinkholes, and Ruberg said they probably are, but he also stated clearly that other options remain. In other words, sinkholes are not merely a dramatic label being pasted onto the discovery. They're a serious hypothesis under active consideration, but not a verdict. That distinction is worth preserving because it keeps the mystery real and the science respectable at the same time. The size issue is especially important. Lake Huron's submerged sinkholes, according to Noah Glerl, can measure hundreds of feet across and up to 60 feet deep, which already places them firmly outside the category of tiny geological inconvenience. But the Lake Michigan depressions reported in 2024 are also on the order of hundreds of feet across and seem unusually neat in outline. When a scientist who already studies Great Lakes sinkholes looks at a new set of features and says, in effect, these might be the same kind of thing but they are larger and weirder in shape, that tells you exactly where the theory stands. It is close enough to be plausible, but different enough to deserve caution. That is often how geology works in real life. A landform belongs to a known family, but its local expression still has enough personality to complicate the family reunion. There is another reason the sinkhole theory remains attractive, and that is what it would imply about water moving through the lakebed. Sinkholes are not just holes. They are evidence of pathways, dissolution, and structural weakness beneath the visible surface. In a karst system, groundwater flow is not incidental. It is the engine of the whole operation. USGS emphasizes that karst hydrogeology is typified by interconnected fissures, fractures, and conduits through which groundwater flow and transport occur. If the Lake Michigan circles are sinkholes, then they are telling scientists something about hidden subsurface plumbing beneath the lake floor. They would imply that water has been interacting with carbonate rock below the sanctuary, moving through fractures, enlarging cavities, and perhaps still emerging or circulating in ways that could affect the chemistry inside the depressions. A lakebed crater is interesting as shape. It becomes much more interesting as evidence of an active or once active groundwater system. That possibility connects directly to the biological intrigue that made the Lake Huron sinkholes famous beyond geology circles. NOAAGLERL reports that the Lake Huron sinkholes are characterized by high sulfate and low dissolved oxygen, and that they are dominated by single-celled microorganisms while lacking the typical fish and metazoan communities found in surrounding lake waters. The NOAA blog on those sinkholes adds that groundwater seeping in has chemistry ideal for microbial survival, with low oxygen and high chloride and sulfate, and that dense microbial mats can develop across the lake floor there. If the Lake Michigan features are indeed sinkholes produced by groundwater moving through soluble bedrock, then one of the next scientific questions becomes whether they also host unusual chemistry and unusual life. That is not proof of the sinkhole theory, but it is one reason researchers care so much about testing it properly. A geological explanation here could carry ecological consequences with it. From a research standpoint, confirming the sinkhole theory would require more than looking at the shape and nodding thoughtfully. Scientists would want to know what kind of bedrock sits under and around the depressions, whether groundwater is entering them, what the water chemistry looks like near the bottom, and whether the sediments or exposed materials inside the holes match a collapse origin. Because karst sinkholes are tied to dissolution and void formation, evidence of carbonate bedrock, subsurface fractures, seepage, and chemical gradients would all strengthen the case. The same Lake Huron projects that made the comparison possible also show what a real investigation looks like. Groundwater chemistry sampling, groundwater flow measurements, and mapping of physical, chemical, and biological processes in and around the sinkholes. Lake Michigan circles are still early in that process. At the moment, shape and setting point towards sinkholes. Detailed confirmation still needs to be earned. The most appealing thing about the sinkhole theory is that it explains several features at once without requiring anything exotic. It accounts for why the depressions could be circular, why they might line up if they are following structural weaknesses in the bedrock, why they sit in a region with appropriate geology, and why researchers immediately thought of Lake Huron. It also fits the broader history of karst, where landscapes that look solid from above can be quietly undermined from below until collapse finally reveals the hidden architecture. There is something satisfying about that, because it turns an eerie visual pattern into the surface expression of a long geological process. The lake floor, under this theory, is not acting strange for no reason. It is revealing the consequences of water moving through old carbonate rock over immense timescales. That is less theatrical than some people would like, but geology usually wins by being patient rather than flashy. Even so, the theory does not explain everything neatly yet, and that is where it stays interesting. If these are classic submerged sinkholes, why do they look so unusually circular? Why do they seem larger than the Lake Huron examples that researchers know better? Are they collapse structures formed in exactly the same way? Or are they related to some broader combination of karst, buried sediment, groundwater pressure, and ancient physical reshaping of the basin? Ruber himself left room for alternatives, and that room matters because the Great Lakes were not formed by bedrock chemistry alone. They were also heavily reshaped by glaciation. Any serious attempt to explain the circles has to remember that older soluble rock sits beneath a landscape profoundly modified by ice. The sinkhole theory may be the best place to start, but once you start thinking about what glaciers do to basins, sediments, drainage patterns, and buried structure, the story underneath the lake gets a little more complicated. If the sinkhole theory gives us one strong way to think about those circles on the floor of Lake Michigan, the glacial story explains why that theory cannot be separated from the longer history of the basin itself. The holes were not found in untouched bedrock that has sat quietly since the age of dinosaurs, and they were not discovered in a landscape that escaped the last ice age. Lake Michigan, like the other Great Lakes, is part of a region shaped in a major way by the Laurentide ice sheet during the last glacial period. NOAA's Great Lakes overview says the mile-thick Laurentide ice sheet covered most of Canada and the northern contiguous United States during the last ice age, and USGS work describes the basins of Lakes Michigan, Huron, Erie and Ontario as having been sculpted in large part by glacial erosion of Paleozoic rocks. That means any explanation for the mysterious depressions has to reckon with ice, because the lake basin itself is already an Ice Age product, before we even begin arguing about circles in the dark. That background matters more than it might first seem. When people hear that glaciers form the Great Lakes, they often picture a simple scene of ice scraping out a hollow and meltwater filling it. The real story is more layered. The bedrock beneath the region already mattered before the ice arrived in full force. Glacial erosion did not act on blank material. It worked across older sedimentary rocks, including shale and carbonate units, and it tended to deepen or exploit the weaker parts of the landscape. One USGS source notes that glacial erosion in western Lake Michigan produced a relatively smooth, gently dipping lake floor, while eastern Lake Michigan is more rugged because of the way the rocks are arranged and eroded. That is a useful detail for this mystery, because the strange craters lie off the Wisconsin side of the lake, in the generally smoother western floor, where unusually neat circular depressions would stand out even more sharply against the broader underwater terrain. Then there is the specific ice stream that shaped this part of the world. Glacial geologists refer to the Lake Michigan lobe, which was one arm of the Laurentide ice sheet moving down the Lake Michigan basin. USGS research on deglaciation calls it the Lake Michigan lobe of the south-central Laurentide ice sheet, and Wisconsin glacial mapping notes that ice was funneled down the Lake Michigan basin into southern Illinois. At the last glacial maximum, parts of what is now the basin were buried below thick glacier ice. That is not just a dramatic image. It tells you that enormous pressure, moving ice, basal debris, meltwater, and repeated advances and retreats all participated in shaping the lake's structure. The holes discovered today may be much younger than that phase of active glaciation, or they may owe their final form to later processes, but the ice laid down the conditions under which those later processes had to work. Once the ice began to retreat, the Lake Michigan basin did not simply become the modern lake overnight. USGS research on Lake Michigan's post-glacial history describes a sequence of large lake-level changes beginning about 11,200 years ago, after the retreat of the Two Rivers Glacier, with later reversals linked to inflows from glacial lake agassiz and additional changes driven by outlet shifts and isostatic rebound. In plain terms, the basin went through a complicated transition from ice-filled to water-filled, with shorelines moving, outlets opening and closing, and water levels rising and falling by very large amounts. At one point during the Chippewa low phase, lake level in the southern basin stood about 80 metres lower than it does today. That means parts of the basin now submerged were once exposed or affected very differently by drainage, erosion, sediment transport and groundwater conditions than they are now. A depression on the modern lake floor may therefore sit in a place that has lived several very different geological lives since the ice retreated. This is where the glacial story becomes especially relevant to the mysterious holes. Glaciers do not just carve basins, they also leave behind a messy inheritance of till, outwash, lake sediments, buried channels, and irregular deposits draped over the older bedrock. USGS work on the central Great Lakes says glacial drift overlies most bedrock in the basin and consists of unsorted till, as well as sorted and layered deposits. Another USGS report describes glacial stream valleys and glacial lake basins being filled with sorted and layered deposits during different ice advances, producing what it calls an underground maze of deposits. That kind of legacy matters because it can control how groundwater moves, where sediment is thick or thin, and where deeper bedrock weaknesses are either concealed or concentrated. In other words, even if the circular depressions turn out to be sinkholes in limestone, the route to that collapse may have been guided in part by the glacial materials left on top. It is tempting at this point to wonder whether the circles themselves might be direct glacial features rather than sinkholes at all, and there is a reason that idea comes up so quickly in Wisconsin. The state is full of landforms made by buried ice. USGS's glacier terminology glossary defines a kettle as a depression formed when a detached block of glacier ice becomes buried in glacial sediment and then melts, enlarging the depression. Wisconsin's own glacial landscape material makes the same point in more local terms. Large blocks of ice broke off, became buried in till, and later melted, leaving kettles, some of them very deep. Those kettle depressions can indeed be circular or crater-like, which is why the comparison is hard to resist the moment anyone starts talking about mysterious holes with an Ice Age connection. But this is also where caution becomes important again. A kettle is not the same thing as a bedrock sinkhole, and the known kettles of glacial terrain are usually associated with outwash plains, moraines, or other unconsolidated deposits left by retreating ice. The Lake Michigan features by contrast are deep underwater, unusually large, and were described in reporting as depressions in or associated with the limestone layer on the bottom of the lake. Steve Ruber also said they were discovered in a hunt for shipwrecks and looked similar to sinkhole-like depressions in the limestone floor, while cautioning that they are bigger and more strangely circular than the Lake Huron examples. So the glacial analogy is useful, but only up to a point. These are not simple textbook kettles sitting in a farmer's field. If buried ice played any role, it likely did so as part of a longer chain of events involving glacial deposits, later flooding, groundwater movement, and bedrock structure, rather than as a neat one-step explanation. A more careful way to say it is this: glaciers may have set the stage even if they did not directly cut the circles we see now. That is an inference, but it is a grounded one. Ice erosion shaped the basin. Glacial retreat left a patchwork of sediments and structural irregularities. Post-glacial lake level changes repeatedly altered hydraulic conditions. Isostatic rebound lifted outlets and changed gradients through time. All of those factors can influence where groundwater flows and where pressure differences persist. Since karst sinkholes depend on groundwater dissolving carbonate bedrock, a glacially modified basin can strongly influence where later sinkholes are most likely to develop. In that sense, the Ice Age may not be the final sculpture of each depression, but it may have arranged the plumbing, loading and sediment cover that made those depressions possible in the first place. There is another reason the glacial past keeps returning to this story, and that is the way deglaciation produces its own local collapse features. USGS research on deglaciation of the Lake Michigan lobe uses sediments in ice-walled lakes to reconstruct a retreat, and one of those landforms is described as a semicircular basin, about 0.72 kilometers wide, inset into till and formed by a 4 to 16 meter thick succession of loess and lacustrine sediment. That does not prove the Lake Michigan holes are related to former ice-walled basins, but it does show that retreating glacier margins can leave behind semicircular depressions of substantial size in the broader Lake Michigan region. The end of glaciation was not a neat, evenly melting process. It involved stagnating ice, readvances, buried blocks, meltwater, and collapse. That means the geometry of a retreat itself can leave rounded features in the landscape, some of which later become buried, flooded, or modified beyond easy recognition. What makes the lake floor mystery more difficult is that the modern basin has had thousands of years to rework whatever glaciation left behind. USGS seismic and core work from southern Lake Michigan shows that the basin records till ice contact drift, outwash, glaciolacustrine deposits, and later non-glacial lacustrine sediments. In other words, the floor of the lake is not a frozen snapshot of one moment. It is a stacked archive. Ice laid something down, meltwater reshaped it, lake water buried parts of it, and later currents and chemistry modified it again. So even if the holes have some ancient glacial ancestry, the visible depressions today could be composite features, partly inherited, partly enlarged, and partly sharpened by later processes. The basin has had ample time to edit its own history. That is one reason scientists are reluctant to make a clean declaration too early. They may be looking at the end result of multiple episodes layered on top of one another. The local Wisconsin setting strengthens that possibility. The state's glacial history is famous for landscapes where two lobes interacted, where buried ice remained after surrounding areas deglaciated, and where collapse created pitted or hummocky terrain. The Kettle Moraine, for example, formed in a zone where large detached blocks of ice became buried and later melted, leaving crater-like depressions. Glacial mapping for southern Wisconsin also notes how the Lake Michigan and Green Bay lobes influenced each other, and how the Lake Michigan basin funneled ice southward. Even though the mysterious holes are offshore rather than in the classic onshore Kettle Moraine, they exist in a region where ice behaviour was anything but simple. That makes it scientifically reasonable to keep glacial inheritance in the conversation, especially when trying to explain why multiple large circular depressions might appear in a line rather than as isolated accidents. At the same time, the Lake Huron comparison keeps pulling the argument back toward groundwater and karst. NOAA's Lake Huron sinkhole project describes those habitats as low oxygen, high sulfate environments linked to submerged sinkholes, and WUWM's reporting says the Lake Huron sinkholes formed where groundwater eroded limestone, created caverns and then caused collapse. That does not erase the glacial past. It simply suggests a sequence in which the glacier's legacy and groundwater's chemistry work together rather than compete. The ice shaped the basin and left the deposits. The later groundwater found pathways through a carbonate landscape. Collapse followed where conditions allowed it. If the Lake Michigan circles turn out to fit that broader pattern, then the Ice Age would still be part of the story, just not the final sentence of it. This is also why a direct glacier did it explanation feels too short, even if it sounds satisfying at first. Glaciers are excellent at making broad basins, scoured surfaces, moraines, kettles, and other landforms that have obvious regional signatures. The mysterious holes off Sheboygan, however, are being discussed because they are not merely broad Ice Age roughness. They are unusually circular, repeated, and striking enough that even researchers familiar with Great Lakes sinkholes said they looked odd. If a landform stands out from the general glacial texture of the western Lake Michigan floor, then the best explanation may involve ice as background and some more focused later process as the finishing tool. That finishing tool could still be bedrock collapse, upward seepage, gas escape, or some combination nobody has nailed down yet. But the glacial past remains in the room because it prepared the conditions under which any of those later processes had to operate. There is a practical side to this as well. When scientists plan the next phases of study, the glacial history tells them what to look for. If the holes are connected to inherited glacial structure, then sediment thickness, buried channels, and glacial stratigraphy around the depressions will matter. If the holes are mainly karst collapse features, then bedrock mapping, seepage chemistry, and groundwater pathways will matter more. Most likely, both sets of questions belong in the same investigation. The basin was built through glacial erosion and deglaciation, then altered through post-glacial hydrology and chemistry. The cleanest explanation may end up being a mixed one. Ice shaped the basin, lake history reworked it, and a later process exploited exactly the places the Ice Age had already made vulnerable. That is not a dramatic answer in the flashy sense, but it is the kind of answer geology often prefers because it lets several pieces of evidence belong to the same story. So when people hear glacial past in connection with these craters, the most useful meaning is not that a glacier simply punched out 40 neat circles and left. It is that Lake Michigan is an inherited Ice Age basin whose bedrock, sediments, drainage history, and even present-day underwater surfaces still carry the marks of that past. The ice determined the basin's broad shape. Retreat and stagnation created irregular landforms and deposits. Lake level changes and rebound altered hydraulic gradients. Groundwater later moved through a landscape the glacier had already rearranged. By the time modern researchers passed overhead with sonar, the circles they found may have been the visible expression of all those older events stacked together, which is why the next step in the story moves naturally away from what ice almost certainly did shape, and toward the harder possibility that even after accounting for glaciers and sinkholes, something about these depressions may still not fit neatly into either box. Once the sinkhole idea is on the table, another possibility begins to press in from the side, not because it is more dramatic, but because the actual shapes on the lake floor leave enough room for doubt. This is the point where geology becomes careful again. The holes in Lake Michigan may indeed be sinkholes, and that remains the leading explanation in much of the reporting, but the researchers involved have not closed the case. Steve Ruberg of NOAA's Great Lakes Environmental Research Laboratory said plainly that he was not yet ready to call them the same kind of sinkholes seen in Lake Huron, because these Lake Michigan features are bigger and very strangely circular. That line matters because it tells you the mystery is not being kept alive for effect. The uncertainty comes from the features themselves. They do not only resemble something known, they also resist fitting into that known category cleanly. That is where the thought of an unknown, or at least not yet confirmed process becomes useful. Not supernatural, not impossible, just not settled. In the more restrained scientific sense, an unknown process often means one of three things. It may mean that the main explanation is right but incomplete. It may mean that several processes worked together and left one final shape. Or it may mean that researchers are looking at a category of lake floor feature that resembles one familiar thing while actually belonging to another. In this case, the alternative most often raised is not a meteor strike, an ancient machine, or anything else that would make a producer rub their hands together too quickly. It is fluid movement through sediment, whether water moving upward from below or gas escaping from trapped pockets in the lakebed. That sounds less cinematic, but in geological terms it is serious, and it has a name that shows up in both marine and lake research: Pockmarks. Pockmarks are not fringe geology. A USGS-linked review describes them as features found in seas, oceans and lakes in many different geological settings, ranging in size from small units only a few meters across to normal pockmarks up to 700 meters wide and as much as 45 meters deep. That same review treats them as signs of hydraulically active seabeds, often associated with fluid flow, gas movement, slides, and other subsurface processes. Frontier's research on lakes says the same thing more directly. Pockmarks are crater-like depressions formed by upward fluid flow of gas and or liquid through unconsolidated sediments on the floor of oceans and lakes. In plain language, if fluid rises from below and disturbs or liquefies sediment strongly enough, the bottom can end up with a circular or crater-like depression. That means a lakebed crater does not have to begin with a dissolved cavern in bedrock. It can also begin with pressure from beneath. That possibility matters here because one of the people involved in the Lake Michigan work, shipwreck hunter Brendan Baylod, suggested exactly that kind of alternative. In Live Sciences reporting, he said the features might be more accurately called craters, formed in deep-bottom sediment by either water upwelling from below or trapped hydrocarbon off-gassing. Smithsonian repeated the same possibility in its summary of the discovery. This is not the same as a formal published conclusion, and it should not be treated as one, but it is still important because it points to a real geological family of processes. Baylod was not tossing out a random idea to keep the story lively. He was naming two mechanisms that geologists already know can shape crater-like depressions in sediment-rich underwater settings. Once that suggestion is made, the Lake Michigan holes stop being a simple two-option puzzle of sinkhole or nothing. They open into a wider field of sediment-fluid interactions. The water upwelling idea is especially interesting because it overlaps with the sinkhole story, without being identical to it. In some lake systems, giant pockmarks are connected to groundwater discharge rather than collapse alone. A 2020 Frontier study of Lake Neuchâtel in Switzerland described giant pockmarks as circular depressions 80 to 150 meters across, linked to active groundwater discharge from a nearby karst system. The researchers found evidence of groundwater in pockmark chimneys, conductivity anomalies, and mini-mud volcanoes visible in ROV imagery, and they concluded that the pockmarks functioned as subaquatic springs connecting the lake to groundwater. That is a very useful comparison because it shows that circular depressions in lakes can be tied not only to collapse, but to ongoing hydrologic exchange. The hole is not merely what happened when something gave way. It can also be the visible mouth of a system still moving water. Another Frontier study from Lake Thun pushes that point even further. It found multiple pockmark systems in one lake, with different morphologies and different likely formation mechanisms. One pockmark there was associated with episodic groundwater seepage near a major karst system. Another group of smaller pockmarks appeared to be actively releasing methane bubbles. A third site included large pockmarks linked to gypsum-bearing bedrock and possible groundwater discharge during intense precipitation periods. The study's broader point is the one that matters most for Lake Michigan. A single lake can contain several kinds of pockmarks shaped by different hydrological and biogeochemical regimes. That means researchers do not have to choose between one universal mechanism and complete confusion. A crater field may belong to a whole class of similar-looking features whose formation paths differ from site to site. The same shape can emerge from more than one underwater story. That is where the mystery becomes more satisfying rather than less. If the holes are not simple sinkholes, that does not make them inexplicable. It makes them part of a larger and more complicated lake floor language that researchers are still learning to read. Pockmarks in lakes have been described as virtually unexplored, compared with marine examples, largely because high-resolution hydroacoustic surveys have historically been used more heavily in oceans than in inland waters. That line from the Lake Thun work is useful because it explains why an enormous, well-known lake can still surprise experts with a whole field of crater-like depressions. It is not only that the features are strange, it is also that the category itself has probably been under-detected in lakes. Once better mapping arrives, the floor stops looking plain and starts showing evidence of processes that may have been there for a very long time. Now, the hydrocarbon off-gassing idea sounds like the one most likely to be sensationalized, so it helps to slow that down. In pockmark geology, gas escape is a standard explanation, not an exotic one. The Frontiers Lake Thun study describes methane-liberating pockmarks, and a USGS-linked review on pockmarks treats them as indicators of fluid flow that can be associated with gas-rich settings. Another geoscience study on pockmarks notes that such depressions are among the most widespread morphologies linked to seafloor fluid flow, and that their formation mechanisms are still not completely constrained because the controlling conditions vary from place to place. In other words, the idea that buried gas pressure could help create crater-like forms in sediment is established in general geology. The question is not whether gas can ever do this. The question is whether it is doing this here, in this specific part of Lake Michigan, at this specific scale. And that is where the current evidence becomes cautious again. Live Science reported that the recent Lake Michigan survey found no water escaping from the holes that would clearly indicate groundwater circulating beneath the lakebed, though Ruberg said he still expected some circulation would eventually be detected. That absence does not rule out groundwater or gas entirely. It simply means the follow-up survey did not catch a clear active seep during that visit. Active fluid systems can be episodic, subtle, or hidden beneath sediments in ways that are not obvious from one inspection. The Lake Thun research, for example, specifically notes that some pockmarks may be only episodically active, with seepage induced by floods, snowmelt, or other conditions. So a lack of obvious bubbling or flow in one expedition is informative but not definitive. It tells researchers what they did not see that day, not what the lake floor is incapable of doing. There is also a scale issue that keeps everything slightly off balance, and it is one reason the phrase unknown process does not feel exaggerated. The Lake Michigan depressions are commonly described as roughly 300 to 600 feet across, with some reports framing many of them in even broader terms. Giant lacustrine pockmarks are known elsewhere, but they remain unusual enough that every new field tends to invite site-specific explanation rather than instant classification. The Lake Neuchâtel pockmarks were 80 to 150 metres across, which overlaps broadly with the lower end of the Lake Michigan range once the units are converted, but the Neuchâtel examples were tied to clearly observed groundwater signatures. The Lake Michigan field, by contrast, has compelling morphology and context, but no equally clear process signature yet. It is the difference between saying, "this kind of thing exists," and saying, "this is exactly that thing." Science is still standing somewhere between those two sentences. A further complication is the sediment itself. Pockmarks, by definition, are usually discussed as features formed through unconsolidated sediments, while the sinkhole idea emphasises dissolution of bedrock and later collapse. But those are not always cleanly separated worlds. In many basins, there is sediment over bedrock, and whatever happens below can influence what the sediment above eventually does. Groundwater can exploit fractures in carbonate rock, gases can accumulate beneath fine-grained layers, and pressure changes can destabilise the overlying column. The Frontier's Pockmark work mentions capillary seals, gas accumulation beneath fine sediment layers, and upward propagating chimneys that can liquefy sediments and evacuate material. That means a lakebed crater could, in principle, reflect both deep structural conditions and shallower sediment response. The final shape might be the surface expression of several stacked processes rather than a single neat event. That mixed possibility becomes even more appealing when you remember where these holes sit. They are in a basin shaped by glaciation, underlain partly by soluble carbonate geology, and covered in places by glacial and post-glacial sediments. That is exactly the kind of layered environment where simple labels can run into trouble. If the basin inherited weak zones, buried channels, variable sediment cover, and pathways for groundwater, then upward water movement, gas escape, and collapse do not have to be rivals. They can be neighbours. One process could prepare the conditions for another. A weakened bedrock zone could localise groundwater. Groundwater could alter sediment chemistry or pressure. Gas could accumulate beneath finer-grained layers. A crater might then reflect not a single cause but a sequence. That is not a dodge. It is often how real basins behave when enough history has been piled into one place. There's also one small but useful reality check on the hydrocarbon idea. A 2026 Elementa paper summarised by USGS reported that new soil atmosphere methane measurements across a large portion of the Michigan basin suggested geologic methane microseepage was non-existent in the sampled region and likely negligible overall at that broad basin scale. The same USGS summary also notes that concentrated seeps from the lake floor were negligible in the earlier context cited by the paper. That does not disprove localised gas-related activity beneath a specific patch of Lake Michigan sediment, because diffuse basin-wide microseepage and localised submerged pockets are not the same thing. But it does argue against treating hydrocarbon escape as an obvious basin-wide default explanation. If trapped gas is involved in these craters, the evidence for it still needs to be found directly in this setting, rather than borrowed from a general sense that Michigan has hydrocarbons somewhere underground. That is why the most honest version of the story right now sounds a little less decisive than people often prefer. Researchers have a field of giant circular depressions in deep water. A sinkhole explanation is plausible because Lake Michigan partly sits on limestone, and similar depressions in Lake Huron turned out to be sinkholes. At the same time, some observers involved in the discovery have suggested that the features may be better described as craters in sediment created by upwelling water or trapped hydrocarbon off-gassing. The broader scientific literature shows that both groundwater-driven and gas-driven pockmarks do occur in lakes, that such features can be large, and that their exact mechanisms often vary from site to site. The current Lake Michigan evidence has not yet pinned one of those mechanisms down. So, unknown process does not mean anything goes. It means several realistic geological explanations remain live at once. In a way, that makes the discovery better. A solved sinkhole story would already be interesting, but a crater field that might involve collapse, seepage, sediment liquefaction, buried gas, or some combination of them all is more revealing about how little of the lake floor we usually picture correctly. It reminds you that underwater landscapes are not passive. They breathe, leak, dissolve, compact, and shift. Even when nothing dramatic is visible from the surface, the bottom can still be responding to forces moving slowly through rock and sediment below. That is one reason crater fields and pockmarks matter so much in other environments as well. Researchers treat them as clues to hydraulic activity, chemical exchange and structural weakness, not just as odd shapes on a map. Lake Michigan circles may end up telling that kind of story too. And then there is the biological side, which keeps quietly pulling this whole puzzle beyond pure geology. The moment you start considering groundwater discharge, gas escape, or fluid seepage, you also have to consider what those things do to local chemistry. In other lake and marine settings, pockmarks and seep areas can alter nutrients, conductivity, redox conditions, and microbial activity. The Lake Neuchâtel study describes pockmarks as subaquatic springs connecting the lake to groundwater, while the Lake Thun work emphasises that pockmarks may influence hydrological and methane budgets in lakes. That means the unknown process question is not only about origin, it is also about ongoing role. A crater may be a relic of something ancient, or it may be a doorway through which the subsurface still interacts with the lake above in ways that change life inside and around it. So for now, the most useful answer is a calm one. Yes, an unknown process could be at work, though unknown here really means not yet distinguished among several grounded options. The circles may prove to be sinkholes after further chemical and geological study. They may instead turn out to be pockmark-like craters formed by upward water movement, gas escape, or both. They may even be hybrid features, shaped by older basin history and then sharpened by later seepage. What researchers do know is that the holes are real, large, repeated, and odd enough to resist a quick label. And once a lake floor starts doing that, the next question becomes less about what were to pin on the depression and more about what kind of environment such a depression creates once it has been there for a long time in the cold, dark water below. What makes these craters more than a good geological puzzle is that a hole on the bottom of a lake can change the water inside it, the sediment beneath it, and the life that manages to persist there. Shape gets attention first because shape is what sonar sees. Chemistry comes next because chemistry decides whether a depression is just an empty dip in the floor or a separate little world with its own rules. That is where this story becomes more interesting. Researchers have not yet published the same kind of detailed chemistry profile for the Lake Michigan craters that already exist for the better studied sinkholes in Lake Huron, so a lot of the excitement here is still based on analogy rather than final proof. But that analogy is strong enough to matter, because the Lake Huron sites show what can happen when unusual groundwater and unusual bedrock combine beneath a Great Lake. In ordinary lake water, especially the kind most people picture when they think of a healthy freshwater system, there is enough oxygen in the water column to support the usual cast of fish, invertebrates, and other organisms. Nutrients move around, sediments settle, and the chemistry changes from season to season, but it still stays within the broad range familiar to lake ecology. The underwater sinkholes in Lake Huron are different enough that scientists have been treating them almost like separate environments tucked inside the larger lake, and NOAA's Lake Huron Sinkhole project says these habitats are characterized by high sulfate and low dissolved oxygen, and are dominated by single-celled microorganisms rather than the typical fish and animal communities found in the surrounding lake. That is a major shift from deep hole to chemically distinct habitat. The reason that chemical shift happens is tied to groundwater. In the Lake Huron sinkholes, groundwater seeps up through the floor carrying a very different chemical signature from the water above it. NOAA's GLERL blog explains that the groundwater there has low oxygen and lots of chloride and sulfate, which come from dissolved limestone underlying the lake. The older Nature Education review on those sinkholes adds more detail, noting that the venting groundwater had no oxygen, lower redox potential, lower pH, lower dissolved organic carbon and nitrate, and higher dissolved inorganic carbon, chloride, and carbonate ions compared with the normal lake water. That is not a tiny adjustment. It is the kind of chemistry package that changes who can live there and how energy moves through the system. There is also a physical consequence to that chemistry. The same Nature review explains that this cold, oxygen-poor, ion-rich groundwater is denser than the lake water around it, so it forms a distinct layer on the lake floor that can be as much as 5 meters thick before gradually thinning away from the source. That is one of the most useful details in the whole discussion, because it means a submerged sinkhole is not just a place where strange water appears and instantly mixes away. The chemistry can hug the bottom and stay concentrated enough to create local conditions very different from those a few meters above. If something similar is happening in Lake Michigan, then the craters may not just be geological forms, they may be chemistry traps, places where denser, mineral-rich bottom water lingers and creates a habitat with rules that differ from the broader lake. That kind of bottom-hugging layer is not especially welcoming to most of the animals people associate with a large freshwater lake. The Nature Review says common freshwater organisms from oxygenated Great Lakes habitats cannot survive in that dense, oxygen-poor layer in Lake Huron, and NOAA's GLERL project says the sinkholes there lack the typical fish and metazoan communities found elsewhere in the lake. The GLERL blog puts it even more plainly. The chemistry is inhospitable for fish and many other forms of wildlife, which gives microbes much less competition and lets them become abundant enough to cover the bottom in colourful mats. That is a useful reminder that chemistry can shape an ecosystem long before anything dramatic happens at the level of visible animals. A place may look quiet on camera while being chemically selective in a very strict way, and this is where the story gets nicely strange. In the Lake Huron sinkholes, those microbes do not appear as a faint smear of life that you need to squint at respectfully. They can form bright, visible mats that spread across the floor in purple, white and green layers. NOAA's GLERL blog describes purple, green and white microbial mats covering the lake floor like a colourful carpet, and the Nature Review identifies the mat-building community as mainly purple, filamentous photosynthetic organisms, along with white non-photosynthetic bacteria and other microbes. In other words, when the chemistry becomes extreme enough and stable enough, microbes are not reduced to a background detail. They become the main landscape feature. The floor stops looking like bare sediment and starts looking like something has painted it, for biological reasons rather than decorative ones, which is probably the best possible reason if we are being fair to the microbes. What those microbes are doing is even more interesting than what they look like. In the shallow, better-lit Lake Huron sinkholes, some of the mat organisms can use sunlight, but not in the simple, plant-like way most people expect. The Nature Review explains that these microbial communities are vertically stratified and metabolically diverse, combining phototrophic, chemotrophic, and heterotrophic layers. Some perform oxygenic photosynthesis, which uses water and produces oxygen. Others can perform anoxygenic photosynthesis, which uses sulfide instead of water and does not produce oxygen. Others still use chemosynthesis, gathering energy directly from inorganic chemicals such as sulfide rather than from light. That means the chemistry of the water and sediment is not just a background condition. It is the energy source and the organising principle for the whole microbial community. That sulfur part is especially important. The same nature source explains that in the sinkholes, some microbes convert groundwater sulfate into sulfide, while others convert sulfide back into sulfate. During the day, certain cyanobacteria can move upward and make use of light. During the night, white sulfur-oxidizing bacteria spread over the mat surface, consuming sulfide and oxygen and producing sulfuric acid as a byproduct. NOAA's Thunder Bay Sanctuary article describes this in a more digestible way, saying purple cyanobacteria may migrate upward during the day toward light. White cyanobacteria remain deeper and use sulfur for energy, and some green microbes can switch between strategies depending on sulfur availability. So the mat is not just alive, it is busy. It is chemically cycling sulfur and carbon all the time, with different microbes taking over under different conditions. This is one reason scientists keep talking about these sites with such respect. The sinkholes are not just low oxygen pockets. They are highly organised systems where chemistry determines which metabolisms work, which microbes win, and when the visible surface of the mat changes. A 2023 Great Lakes research paper summarised in Science Direct describes the Lake Huron sinkhole mats as modern-day communities resembling early Earth, and notes that photosynthesizing cyanobacteria and sulfur-oxidizing bacteria move in response to daily changes in light and chemistry, making the matte surface appear purple by day and white by night. That sounds almost theatrical, but it is just metabolism on a schedule. The microbes are not trying to impress anyone. They are responding to gradients in light, sulfide and oxygen the way any living system responds to usable energy. There is an even deeper layer to this chemistry, and it lives down in the sediment. The Nature Review notes that sulfate reduction in the sediment produces sulfide, and that once oxygen and sulfate are depleted, fermentation and methanogenesis can take over. It also says methane gas can be produced by archaea in the sediment and can become trapped under the microbial mat, helping create finger-like protrusions. NOAA's GLERL blog gives a matching visual description, explaining that small hills and fingers in the Lake Huron mats are caused by gases like methane and hydrogen sulfide bubbling up beneath them. So when researchers talk about strange chemistry in these environments, they are not referring to a slightly unusual water sample. They mean a whole system where dissolved minerals, redox gradients, sulfur cycling, gas production, and microbial architecture all feed into one another. Now bring that back to Lake Michigan, and the key thing is honesty. Scientists have not yet shown that the newly found craters host the same chemistry. They have not yet published evidence that sulfate-rich groundwater is venting there in the same way. They have not yet shown dense microbial mats carpeting the bottom the way Lake Huron's best-known sinkholes do. What they do have is a set of large, cold, dark depressions in a lake that sits partly on limestone and that already has a close Great Lakes analogue, where unusual groundwater chemistry creates unusual ecosystems. Smithsonian's reporting on the Lake Michigan craters says the depressions are dark, chilly, and mostly devoid of oxygen, and that scientists suspect specially adapted bacteria may also live there because similar bacteria live in Lake Huron sinkholes, but they plan to investigate further to confirm. That is exactly the right level of caution. The chemistry is a possibility, not yet a settled fact. There are a few signs, though, that make the chemistry question worth taking seriously rather than filing under interesting later. The recent surveys of the Lake Michigan craters captured freshwater shrimp, small fish, and invasive quagga mussels, showing that the depressions are not sterile voids. At the same time, Live Science reported that researchers did not observe water escaping from the holes during that survey in a way that would clearly indicate groundwater circulating beneath the lakebed, though Steve Ruberg said he expects some circulation will eventually be detected. That is a very specific kind of uncertainty. It does not tell us the craters are chemically ordinary. It tells us that one obvious sign of active seepage was not caught on that visit. In lake floor chemistry, timing matters. A system can be subtle, episodic, or hidden in the sediments in ways that do not announce themselves on command. And even without a fully documented seep, the depth alone changes the starting conditions. The Lake Michigan craters lie roughly 450 feet below the surface. At that depth, light is gone, temperatures are low, and the biological options narrow. If unusual groundwater or seepage is entering those depressions at all, then the chemistry there could become disproportionately important because there is very little sunlight-driven productivity to overwhelm it. In the deeper Lake Huron sinkholes, NOAA's GLERL blog says some are so deep that sunlight cannot reach them, yet microbes still live there because they get energy from minerals in the water through chemosynthesis. That is why the Lake Michigan craters have such appeal to ecologists and microbiologists. If the chemistry turns out to be unusual, then life inside them may be organised by chemicals first and light second, or not by light at all. That possibility is important because chemistry is often where a geological feature becomes an ecological one. A crater formed by collapse is geology. A crater that channels ion-rich groundwater, alters redox conditions, and supports specialised microbial communities is suddenly ecology, microbiology, and biogeochemistry all at once. NOAA's sinkhole project in Lake Huron explicitly frames the research around understanding the physical, chemical and biological processes in and around the shallow and deep sinkholes. The chemistry is not a side note there. It is the bridge that links bedrock to microbes. If the same kind of bridge exists in Lake Michigan, then the craters may matter not only because they are mysterious, but because they create microenvironments the rest of the lake does not. There is also a practical reason scientists care about low oxygen chemistry beyond simple novelty. Low oxygen, sulfur-rich systems are good places to study metabolisms that do not dominate in ordinary surface waters. In Lake Huron, researchers have used these sinkholes to examine microbial mats, groundwater chemistry, and sulfur cycling precisely because the chemistry strips away the usual lake background and lets the more specialised processes stand out. The Nature Review goes so far as to describe the sinkhole microbes as living analogues of activities performed long ago in oxygen-poor, sulfur-rich seas. NOAA's Thunder Bay Sanctuary article says, "The sinkhole conditions emulate the high-sulfur ocean of early Earth, and that understanding the microbes' movements may help explain how mat-building organisms survived sharply changing chemical conditions and contributed to the rise of oxygen later on. That is not a small scientific payoff from an odd patch of water. Seen that way, the Lake Michigan craters are exciting even before anyone has finished measuring them. They sit at the exact intersection where a geologist, a chemist, and a microbial ecologist all start leaning forward for different reasons. The geologist wants to know how the depression formed. The chemist wants to know whether the water inside it is distinct from the lake above it. The microbial ecologist wants to know whether that chemistry selects for rare or unusually ancient-looking metabolisms. And because these are deep freshwater features in a major Great Lake, rather than exotic vents on the far side of the planet, the whole investigation becomes oddly accessible. You do not need a submersible descending into an ocean trench to find an environment with the potential for very strange chemistry. Sometimes a large Midwestern lake is more than capable of causing trouble on its own. There is one more detail worth holding on to. Chemistry in these systems is not static. Even in Lake Huron, where the sinkholes are much better studied, the mats and gradients change with light, depth, and local conditions. Some communities are sunlit and layered. Others are deep and fully aphotic. Some involve visible movement through the day. Others depend more heavily on dark chemosynthesis and sulfur transformations. That means if Lake Michigan's craters do turn out to host unusual chemistry, the result may not be one simple, "the craters are low oxygen" label. Different holes may differ. The centres may differ from the rims. The sediment may tell a different story from the water immediately above it. The chemistry could be patchy, layered, and active in ways that only become obvious after repeated sampling. In underwater research, one good map is the beginning. One water sample is still just a hint. So when people hear strange chemistry in the crater depths, the safest and most accurate version is this. The Lake Michigan craters have not yet yielded the same detailed chemical story as the Lake Huron sinkholes. But the reason scientists are so interested is that in nearby Great Lakes sinkholes, groundwater rich in sulfate and low in oxygen creates dense bottom layers, suppresses ordinary lake fauna, and supports microbial mats powered by sulfur cycling, chemosynthesis, and other metabolisms that look very different from everyday freshwater life. If even part of that pattern appears in Lake Michigan, then the craters are not just holes. They are chemical environments, and chemical environments of this kind have a habit of pointing beyond the modern lake and into a much older version of Earth, where oxygen was scarce, sulfur mattered more, and microbial life did most of the heavy lifting. If strange chemistry is the part of this story that makes the craters feel alive in a scientific sense, then the next step is understanding why scientists keep connecting places like these to a much older Earth. That comparison is not casual. It is not the sort of thing researchers say because it sounds good in a documentary. The comparison comes from the fact that certain submerged sinkholes in Lake Huron already provide modern environments with low oxygen, high sulfur, and microbial communities that use chemistry in ways more typical of ancient Earth than of the oxygen-rich world most animals now live in. NOAA's sanctuary material describes those sinkholes as a kind of time capsule, and the water in Middle Island sinkhole is sulfur-rich and oxygen-poor enough to serve as a proxy for life on Earth billions of years ago, roughly around the beginning of the Proterozoic eon. That matters because early Earth was not an animal world. It was a microbial world. For a very long stretch of planetary history, oxygen in the atmosphere remained extremely low, and the dominant living systems were single-celled organisms operating in oceans and shallow seas with very different chemistry from the one we know now. NOAA's Thunder Bay overview says the sinkhole conditions emulate the high-sulfur ocean of early Earth, an environment that would have been inhospitable to modern animals but favourable to microbes. The Nature Citable review says much the same thing in more biochemical detail, explaining that the Lake Huron sinkhole mats use sulfur compounds for energy and organic matter production in ways that resemble ancient microbial metabolisms. So when scientists talk about clues to early Earth, they are not saying these lakes preserve dinosaurs or lost oceans. They are saying the chemistry and metabolism inside some of these systems resemble conditions and strategies that were once much more common on the planet. The most direct reason for that comparison is the water itself. In the better-studied Lake Huron sinkholes, groundwater entering the sinkhole floor is low in oxygen and rich in dissolved compounds such as sulfate and chloride. NOAA's Lake Huron sinkhole project describes those habitats as high in sulfate and low in dissolved oxygen, while the Nature Review explains that venting groundwater there has lower oxygen, lower redox potential, and elevated inorganic ions compared with surrounding lake water. That is the sort of chemical setting where microbes that can use sulfur compounds or switch between different metabolic strategies gain a major advantage. On early Earth, long before oxygen became abundant in the atmosphere, those kinds of chemical energy pathways were not unusual edge cases. They were central. A place in the modern world where microbes still thrive under similar constraints is therefore scientifically valuable in a very direct way. There is also a structural reason these places work as analogues. In Lake Huron, the sinkholes are not just random chemical oddities mixed evenly into the lake. They are localized environments where dense, unusual bottom water can remain distinct enough to shape who lives there and how the community functions. The Nature Review describes a dense, oxygen-poor groundwater layer that can rest on the lake floor near the vents before gradually mixing away from the source. That is important because early Earth analogues are not useful simply because they have one unusual number on a lab readout. They are useful when they sustain a coherent living system under those conditions. The Lake Huron sinkholes do that. They create a stable enough chemical setting for sulfur cycling, microbial mat formation, and specialized ecological structure to persist. If the Lake Michigan craters turn out to host similar groundwater inputs or similar bottom chemistry, then they too could become living models for ancient environmental conditions rather than just geological curiosities. This is why the microbial mats matter so much. A mat sounds harmless, almost domestic, like something you would roll up and put near a door. In these systems, it means a layered microbial community spread across the bottom, dense enough to be seen clearly and chemically active enough to drive its own local cycles. NOAA's Thunder Bay article describes purple and white mats draped across sinkholes in Lake Huron, while the Nature Review explains that the mats include organisms performing oxygenic photosynthesis, sulfur oxidation, sulfate reduction, and other linked processes. That combination is exactly what makes them useful as analogues. Early Earth did not rely on forests, fish, or flowering plants to shape global chemistry. It relied heavily on microbial communities interacting with sediment, sunlight, sulfur, carbon, and whatever oxidants were available. In Lake Huron, scientists are not just seeing microbes survive in weird water. They are seeing microbes build an organized, layered community that behaves like a living chemical engine. The sulfur part is not a minor detail. It is one of the main reasons the analogy works at all. The Citable Review says some sinkhole microbes convert sulfate in the groundwater into sulfide, while others convert sulfide back into sulfate. It calls that closely coupled microbial cycling of sulfur and carbon, and explicitly notes that, like on early Earth, These microbes use sulfur molecules for making organic matter and obtaining energy. That sentence does a lot of work. It tells you that the analogue is not based only on low oxygen. Low oxygen by itself can describe many stressed environments. The stronger comparison comes from the combination of low oxygen and active sulfur-based metabolism. Early Earth's oceans are often thought to have included large zones where sulfur chemistry mattered enormously, and these sinkhole systems give researchers a place where that kind of metabolism can still be observed directly, rather than reconstructed only from ancient rocks. Another reason researchers care is that the mats do not just sit there passively. They move and rearrange themselves over the course of a day. A 2023 paper in the Journal of Great Lakes Research reports that modern benthic microbial mats, resembling those of early Earth, inhabit Lake Huron's low oxygen, high sulfur submerged sinkholes, and that researchers observed daily vertical migration of purple cyanobacteria and white sulfur oxidizing bacteria across the mat sediment interface. The broader significance of that finding became even clearer in the 2021 Nature Geoscience study and related summaries from NSF and the University of Michigan. Those works linked mat behaviour and oxygen released to day length, suggesting that longer days on early Earth may have helped increase the amount of oxygen released by microbial mats. That does not mean Lake Huron answers the entire oxygenation puzzle by itself, but it does mean these Great Lakes sinkholes helped scientists test a real hypothesis about one of the largest changes in Earth history. That connection to oxygenation is worth slowing down for a second because it is one of the strongest reasons these sites matter beyond local geology. Earth's atmosphere did not become oxygen-rich all at once. It changed gradually and unevenly over vast stretches of time. The University of Michigan and NSF summaries of the 2021 work explain that longer day length can increase the amount of oxygen released by photosynthetic microbial mats, and that this may help explain the timing and pattern of Earth's oxygenation. In the middle island sinkhole, white sulfur oxidizing bacteria can sit above purple photosynthetic cyanobacteria during low light periods, limiting oxygen production, then move lower when light becomes strong enough, allowing the cyanobacteria to produce more oxygen. That is a remarkably concrete demonstration of how microbial competition, chemistry and physical conditions can affect oxygen release. It takes the question of early Earth out of pure abstraction and puts it into something measurable on a lake floor in Michigan. Seen that way, the analogy to early Earth is not some vague line about harsh conditions and ancient life. It is a specific scientific use of a living system. Researchers study these sinkholes because the microbial communities there can help answer questions about how primitive photosynthesizers and sulfur metabolizing organisms interacted before oxygen became abundant. NOAA's Thunder Bay material says understanding these microbes may provide clues to how mat-building organisms survived sharply changing chemical conditions on early Earth and contributed to the accumulation of oxygen in the atmosphere. That is a very precise reason to care. The sinkholes are not interesting only because they are weird. They are useful because they preserve a metabolically relevant situation that modern surface environments rarely preserve so clearly. This is where the newly found Lake Michigan craters become scientifically tempting. No one has yet shown that they host the same style of low oxygen, sulfur-rich groundwater-fed microbial mats found in Lake Huron. That has to be said plainly. At the moment, the early Earth comparison for Lake Michigan is still an informed possibility, not a confirmed match. But the logic for investigating it is strong. The craters sit in deep, cold water. They may be sinkholes or seep-related depressions. Lake Michigan shares relevant carbonate geology with Lake Huron, and researchers involved in the discovery have already framed the craters as potentially important because similar Great Lakes features host unusual microbial systems. Smithsonian's reporting on the Lake Michigan discovery noted that the craters could hold clues about unusual low-oxygen ecosystems and even conditions similar to those of early Earth, precisely because of what has already been learned from Lake Huron sinkholes. That "could" is the key word, and it is the word good science usually lives on during the early phase of a discovery. the Lake Michigan craters have not yet yielded the same depth of microbial and geochemical characterization. Researchers have not yet shown broad purple and white mats there, nor have they published a full set of measurements proving a sulfur-rich, oxygen-poor groundwater layer. But the comparison is not wishful for that reason. It is predictive. It says, in effect, we know that this class of Great Lakes sinkhole system can create early Earth-like chemical habitats nearby, so now we should test whether this newly discovered crater field does the same. That is how analogues are used properly. They do not erase uncertainty. They tell you what measurements to make next. There is also something useful about the fact that these analogues are freshwater rather than marine. When people hear about ancient Earth, they often imagine remote hydrothermal vents or exotic hot springs, which are of course scientifically important. But the Lake Huron work shows that a cold freshwater system can also preserve metabolisms and community structures that speak directly to early biogeochemical conditions. NOAA's material and the Nature Review both emphasize that the sinkholes are low oxygen, sulfur-influenced microbial habitats underlain by ancient marine evaporates and carbonate rocks. That combination lets researchers ask ancient questions in a modern inland setting, direct access for repeated sampling, diving, ROV imaging, and long-term monitoring. For science, that is a gift. It means you can revisit the same living analogue many times rather than depending only on rare or extreme settings far from shore. There is even a broader astrobiology-style reason people pay attention to systems like these. The microbial mat literature tied to the Great Lakes sinkholes has described them as models not only for early Earth, but for life in low-light or no-light environments more generally. A 2021 review on extant microbial mats treated sulfur-rich, anoxic, aphotic sinkhole ecosystems in Lake Huron as useful models for understanding microbial life under conditions with little to no sunlight. That does not mean scientists are quietly claiming Lake Michigan is an alien world in disguise. It means that once you understand how life persists in chemically driven, oxygen-poor habitats on Earth, you gain a better toolkit for interpreting ancient Earth and other possible habitats where sunlight is weak or absent. The point is not spectacle. The point is method. A strange crater can lead to a very practical question. What kinds of metabolism work here, and what does that tell us about life under similar constraints elsewhere? Still, the early Earth comparison should not be pushed too far. The Great Lakes are not the Archean oceans. They sit beneath a modern atmosphere, contain modern microbes, and exist within a world already reshaped by oxygen, complex life, and continental weathering patterns very different from those of early Earth. What scientists mean by analogue is more limited and more precise. They mean that some of the chemical gradients, energy pathways, and microbial strategies in these sinkholes resemble those believed to have been important on ancient Earth. That is why the term working analogue shows up so often in the research summaries. The Lake Huron sinkholes are useful because they isolate certain conditions and let researchers study them in action. They are not replicas, they are windows, and if the Lake Michigan craters open onto similar chemistry, then they may offer another window, perhaps with their own differences in depth, light regime, size, and microbial structure. One of the more interesting things about these windows is that they are not static museum displays. The Lake Huron sinkholes have already produced changing lines of research. NOAA's project page says scientists have measured physical parameters through time, sampled groundwater chemistry and flow, and collected microbial mat samples for further analysis. The 2023 Deal migration paper used time-lapse observations across multiple years. The 2021 oxygenation study drew on field observations, lab experiments, and modelling. That means early Earth analogues are not just places scientists point at from a boat and admire. They are active research sites that keep yielding new questions. If Lake Michigan's craters turn out to have even part of the same chemical and microbial structure, then they could add a second Great Lakes system to that research tradition and help scientists compare how similar ancient-style metabolisms behave under somewhat different freshwater conditions. For narration, this is probably the most satisfying part of the whole mystery. The holes are interesting on sight, but the reason scientists get genuinely excited is that a depression in the lake floor can become a living experiment in planetary history. You start with sonar and depth, then you find unusual chemistry, then microbes show up with metabolisms that make sense in sulfur-rich, oxygen-poor water. Then suddenly, the crater is no longer only part of Lake Michigan or Lake Huron. It has become a model for how life functioned before animals, before forests, before blue skies look the way they do now. That is a remarkable jump, and it is earned step by step. No single sentence makes it happen. The geology makes the chemistry possible. The chemistry selects the microbes. The microbes make the ancient comparison worth taking seriously. And yet there is something almost funny about where all this leads us. You begin with a familiar American lake, the kind people associate with beaches, harbours, ferries, storms, and stubbornly cold water. You map the floor and find giant circles. You investigate those circles and start wondering about groundwater, sulfur, microbial mats, and Earth's oxygenation history. It is not the route most people expect, but that is part of what makes the Great Lakes so effective at surprising both scientists and everyone else. They look ordinary from the surface in the way very large things often do. Down below they can still preserve settings that point backward far beyond human history and even beyond animal history, which, in its own quiet way, makes the bottom of the lake feel less like a local curiosity and more like a stacked archive where shipwrecks, geology, chemistry, and the earliest forms of life all seem to brush up against one another. And once a place starts doing that, it is not hard to see why the mood around these discoveries drifts from simple science into something a little more uncanny, because the Great Lakes have never really needed much help developing a reputation for holding on to things in the dark. If those cratered hollows on the floor of Lake Michigan seem eerie now, part of the reason is that they do not exist in a blank setting. They sit inside a lake that already carries a very long memory. By the time scientists begin talking about sulfur, low oxygen, microbial mats, and conditions that echo early Earth, the human mind has already begun adding another layer of history on top of the geology, because Lake Michigan is not only a basin of water and rock, it is also one section of a much larger inland corridor where people have travelled, traded, fished, crossed storms, vanished, washed ashore, and in many cases never come back. The Great Lakes have been used for thousands of years as a major route through the heart of North America, and NOAA estimates that around 6,000 shipwrecks lie beneath the 5 lakes, including about 1,200 in Lake Michigan alone. That is an extraordinary number, and it changes the emotional atmosphere immediately. A lake with that many wrecks stops feeling like scenery and starts feeling like an archive, one written in timber, iron, cargo, weather, and silence. That archive is especially vivid along the Wisconsin side where the newly discovered craters were found. Wisconsin Shipwreck Coast National Marine Sanctuary protects 36 historic shipwreck sites, and, according to NOAA, research suggests another 60 may still await discovery inside the sanctuary boundaries. The cold fresh water of Lake Michigan preserves many wrecks with remarkable clarity, which is why NOAA has described the Great Lakes as among the best places in the world to study historic shipwrecks. On this stretch of coast, some vessels remain so well preserved that they still appear almost composed, as if the lake accepted them, settled over them, and then declined to disturb them further. That preservation is part of the uncanniness. Salt water tends to destroy. Lake Michigan in many cases keeps. A wreck does not always become a ruin in the dramatic cinematic sense. Sometimes it becomes a still life. That makes every new sonar image feel slightly double-edged. It might reveal a geological feature, or it might reveal a ship that has been waiting in the dark longer than any living person has been alive. That is one reason Lake Michigan's reputation has always been a little different from the reputation of an ordinary lake. It is not simply that storms happen there, though they do, and often with very little interest in human schedules. It is not simply that navigation on a large inland sea has always been dangerous, though history makes that point repeatedly and without much mercy. It is that the losses are not abstract, they remain present. A steamer can go down in a gale, settle into cold fresh water, and still be there generations later, with enough structure intact to let historians and divers read the final scene in physical detail. Noah's own sanctuary material uses examples like the steamer Vernon, sunk in 1887 with 48 lives lost, and the Rouse Simmons, the famous Christmas tree ship lost with all hands in a November gale in 1912. Those are not half-remembered fables. They are documented tragedies, preserved by the same water that now hides the giant circles on the lake floor. When a place repeatedly turns catastrophe into physical memory, people do not need much encouragement to start speaking of it with a little extra caution in their voices. The preservation of wrecks also creates a strange reversal in how time feels. On land, disaster often gets cleaned up, rebuilt over, or worn down until it becomes mostly narrative. Under Lake Michigan, time can remain visible. NOAA and Wisconsin sources alike emphasize that cold fresh water slows the kinds of decay common in saltwater. Wooden hulls are spared shipworms. Metal often retains detail longer than people expect. Personal objects, cargo, fittings, anchors, and entire deck structures can survive well enough to make the past feel less finished than it should. A wreck discovered today may not feel like something newly created by technology. It may feel like something old deciding to become visible again. That is part of the lake's uncanny reputation too. It does not merely swallow things. From time to time, it gives them back in forms that are calm enough to be unsettling. A good example is the schooner Thomas Hume, one of the most persistent disappearances in Lake Michigan history. The vessel vanished in a squall on May 21, 1891, while carrying lumber from Muskegon to Chicago, and all 6 men aboard were lost. For years, the ship's fate was a genuine mystery. It did not merely sink in a known location and wait for rediscovery. It disappeared from ordinary knowledge and stayed there. Only much later was it found remarkably intact, preserved by the lake rather than shredded by it. That combination is exactly the kind of thing that gives a body of water a reputation. A ship goes missing. Stories accumulate. Decades pass. Then the lake reveals the answer in a form both clarifying and eerie, because the explanation is physical and real, yet the years of absence have already changed the emotional shape of the story. A mystery solved underwater is not the same as a mystery solved on land. The water keeps the atmosphere even after the facts arrive. The same pattern appears again in more recent history, and perhaps nowhere more hauntingly than in the disappearance of Northwest Orient Flight 2501. Shortly after midnight on June 24, 1950, the airliner crashed into southeastern Lake Michigan, killing all 58 passengers and crew. Debris and human remains washed ashore, but the main wreckage was never found. In 2025, after a 20-year modern search effort that covered hundreds of square miles, searchers announced they were ending the campaign without locating the aircraft itself. Think about what that does to the lake's reputation. A storm, a vanished plane, fragments washing ashore, decades of searching, and still no definitive resting place for the wreck. That is not folklore. That is documented 20th century history. Once a lake contains that kind of unresolved loss, it acquires a tone that even calm scientific language cannot entirely wash away. The water stops being only a surface. It becomes a keeper of unfinished locations. From there, it is not surprising that folklore eventually moved in and tried to give the mood a shape. Over time, some writers and local storytellers gathered several disappearances, wrecks, and aviation losses into the idea of a Lake Michigan triangle, a kind of inland echo of the more famous Bermuda version. The triangle's boundaries are usually drawn between Ludington, Manitowoc, and Benton Harbor, and the label has persisted because it offers people a neat outline for a much messier collection of real events. But the important thing is not whether one believes in the triangle as a paranormal zone. The important thing is that the legend exists at all, because it reveals how humans respond when a place accumulates enough true losses, enough partial recoveries, and enough persistent absences. We invent a shape for the unease. We give it a name. We take weather, wrecks, fog, missing aircraft, and old maritime fear, and we arrange them into folklore because folklore is what people make when the facts are heavy and the lake remains larger than their explanations. The truth, of course, does not need help from the paranormal to feel uncanny. The shipping history of Lake Michigan is already crowded with enough storms, navigation errors, sudden gales, icing, collisions, fog and cold water deaths to make the lake feel formidable without assistance from any invisible triangle at all. That is probably the more interesting version anyway. A supernatural explanation can flatten a landscape into a gimmick. Real history keeps it textured. Ships sank here because the lake is large, busy, and capable of turning violent quickly. Planes were lost here because weather over water can shift in dangerous ways, and because not every disaster yields a clean, recoverable wreck. The uncanny reputation of Lake Michigan comes not from magic, but from accumulation. Enough people crossed it. Enough of them failed to make it. Enough of what they left behind remained hidden. Once those conditions are in place, the atmosphere almost rights itself. It also helps that the lake continues to produce discoveries in the present tense. This is not one of those bodies of water whose mysteries all belong comfortably to the 19th century. Even now, wreck hunters using side-scan sonar and remotely operated vehicles are still finding ships long thought lost. In 2025, the schooner F.J. King, lost in 1886 during a storm, was discovered off Bailey's Harbour after nearly 140 years, earning once again the label of a ghost ship. A year earlier, searchers found the wreck of the Margaret A. Muir, another 19th century schooner long missing from ordinary memory. These are the sorts of discoveries that keep the lake's uncanny reputation from fading into pure legend. The past does not stay politely in the past. It surfaces in sonar returns. It reappears in mussel-covered hulls. It turns up because someone makes another pass over the bottom and notices that a shadow on the screen has the geometry of a ship. That kind of continuing recovery keeps the whole lake emotionally active. The archive is still opening. There is a practical urgency behind that too, and in a strange way it adds to the mood rather than reducing it. Researchers are racing to document Great Lakes wrecks, because invasive quagga mussels are increasingly damaging them, burrowing into wood, coating structures, and accelerating corrosion in ways that threaten to erase details that survived for more than a century. AP reported that historians and archaeologists are now trying to capture these wrecks before this modern layer of biological damage destroys what the cold fresh water preserved so well. That means the lake's hidden history is not only hidden, it is fragile. A wreck can wait quietly for 140 years, be found at last, and then immediately become part of a race against deterioration. There is something almost unfair about that, though lakes have never shown much interest in being fair. The result is that every modern expedition carries two moods at once: discovery and rescue. Researchers are not just finding the past, they are trying to record it before it changes again. Once you look at Lake Michigan through that lens, the discovery of those giant circular craters begins to feel as if it belonged here all along. Not because craters and shipwrecks are the same kind of thing, but because both emerge from the same larger pattern. The lake keeps more than we expect. It reveals things slowly. It mixes the scientific, the historical, and the emotional, in a way very few landscapes manage to do without seeming forced. A research vessel heads out to map a sanctuary known for preserved wrecks and maritime loss, and the bottom offers not only ships, but a line of vast circular depressions that may lead towards strange chemistry and microbial worlds. In another setting, that might feel like too many kinds of mystery stacked together. In Lake Michigan, it feels oddly appropriate. This lake has had centuries to practice being larger than the stories people first tell about it. There is also a quieter psychological reason the lake's reputation lingers. Oceans are supposed to be mysterious. That is part of their public role. Lake Michigan is not always granted the same courtesy, which makes its hidden life more effective when it appears. It sits beside cities, farms, harbours, roads, beaches, and ordinary routines. Children skip stones on it. Ferries cross it. People glance at it from condos and parking lots and think they understand the broad arrangement. Then they learn that around 1,200 shipwrecks are believed to lie in this one lake, that preserved vessels still turn up after more than a century, that a major air disaster remains physically unresolved, that Folklore had to invent a triangle to hold the mood, and that scientists mapping the bottom have now found dozens of giant craters whose origin is still under study. At that point, Lake Michigan stops behaving like background. It becomes one of those places that quietly refuses to be exhausted by familiarity. So the lake's uncanny reputation does not have to be argued for very hard. It was built piece by piece. It came from preserved hulls standing in cold darkness as if waiting for inspection. It came from names like Vernon, Rouse Simmons, and Thomas Hume. It came from the debris field of Flight 2501 and the absence that followed. It came from modern searchers still finding ghost ships by sonar, while others admit that some losses may never be physically recovered at all. And it came from the simple fact that, even now, the floor beneath this familiar water continues to reveal new shapes no one expected to see. That's enough to give any lake an eerie reputation, and certainly enough for one that already holds so much wreckage and memory. Which is why those craters matter in a broader way too. Because once a place has spent so long preserving both human loss and geological secrecy, the final question is not only what the holes are, it is what they may mean when the scientific curiosity settles and the data begin to tell us, more plainly than the folklore ever could, what kind of hidden world has been sitting under Lake Michigan all this time. So when all of this is taken together, the circles on the floor of Lake Michigan begin to matter in a very different way. At first, they sound like a neat mystery, the kind of discovery people enjoy because it makes a familiar place seem slightly less familiar. But science does not stop at "that is strange." It immediately asks what kind of knowledge a strange thing can produce. In this case, the answer is quite a lot. The holes may tell researchers something about the hidden geology of the lake basin, about groundwater movement through ancient rock, about how chemistry can reshape ecosystems in deep fresh water, about how much of the Great Lakes still remains unmapped in useful detail, and even about how certain microbial worlds on modern Earth can help us understand much older planetary conditions. That is a long list for a set of depressions in dark water, but it is exactly why discoveries like this attract so much attention once the first surprise wears off. They are not just interesting objects, they are possible entry points into several branches of science at once. The most immediate scientific meaning of the craters is geological. If the features are confirmed as sinkholes, they would strengthen the case that parts of Lake Michigan's floor are shaped by active or former karst processes linked to soluble carbonate bedrock. That would matter because karst terrain is not merely a pattern of holes. It is evidence of water moving through fractures, dissolving rock, enlarging cavities, and changing the structural stability of the ground from below. The US Geological Survey describes karst aquifers as systems characterized by fissures, fractures, conduits, caves, springs, and sinkholes, all formed through the dissolution of rocks such as limestone and dolomite. If the Lake Michigan holes belong to that family, then they would show that the basin floor is recording subsurface plumbing rather than only surface sediment patterns. That would help researchers refine models of bedrock weakness, groundwater flow paths, and the long-term interaction between glacially modified sediments and much older carbonate geology beneath the lake. And even if the holes turn out not to be classic sinkholes in the strictest sense, they still matter scientifically because they may reveal a second kind of hidden process, the movement of water or gas through sediments from below. Research on pockmarks in lakes and marine settings shows that crater-like depressions can form where fluids rise through unconsolidated sediments, sometimes linked to groundwater discharge and sometimes to gas escape. Studies from lakes in Europe have described giant pockmarks connected to active groundwater discharge and other pockmark fields associated with episodic seepage or methane release. That makes the Lake Michigan craters valuable even before their mechanism is nailed down. They offer scientists a real field site where they can test which signals distinguish collapse features from seep-related craters, how sediment responds to pressure from below, and whether multiple processes can create similar-looking circular landforms on a lake floor. In other words, the holes may help refine not only what happened here, but how underwater depressions are classified more broadly. That classification problem is more important than it sounds, because lake floors are often treated as if they should be simpler than ocean floors. In reality, they are just less widely mapped, and in many cases less intensively studied. NOAA's Lakebed 2030 material says only about 15% of the Great Lakes has been mapped at high density so far. That figure is one of the biggest scientific messages hidden inside this story. The holes matter not only because of what they are, but because of what their discovery says about the state of Great Lakes knowledge. A basin that holds about 20% of the world's surface fresh water can still contain large features that most people, and even many experts, have never seen in detail. That means every credible anomaly found by modern mapping is also a reminder that the Great Lakes are still in an exploratory phase. The bottom is not a finished map. It is an active frontier of survey science. That alone gives the craters scientific value, because one discovery can influence how future mapping work is prioritized. NOAA's Sanctuary Science material says mapping in Wisconsin's Shipwreck Coast is used to characterize both cultural and natural features, and NOAA coastal science work on the Wisconsin Lake Michigan coast says lakebed mapping supports monitoring, protection, and management of ecological and cultural resources. When a crater field appears in that context, it changes the practical questions that maps are asked to answer. Researchers are no longer only identifying wrecks, substrates, and habitat types. They're also looking for repeated depressions, structural patterns, possible seep locations, and relationships between basin shape and chemistry. A feature like this can therefore push a mapping program from description into hypothesis testing. That is a significant shift. It means the holes are not just one more interesting mark on a chart. They become reasons to revisit certain depths, collect different kinds of measurements, and build more integrated maps that combine geology, habitat, archaeology, and hydrology, rather than treating those as separate domains. There is also a strong ecological reason the holes matter. A depression on the lake floor can alter local flow, trap denser water, accumulate fine sediment, and create a setting where chemistry differs from the broader water column above. In Lake Huron, submerged sinkholes have already shown how that can happen in dramatic form. NOAA's Great Lakes Environmental Research Laboratory describes those sinkholes as low-oxygen, sulfate-rich habitats dominated by microorganisms rather than the fish and animal communities typical of surrounding lake waters. The chemistry there is not a small difference. It is enough to create dense microbial mats and make the sinkholes function like chemically distinct environments inside the larger lake. If even a weaker version of that pattern exists in Lake Michigan's craters, then each depression may represent not only a landform but a habitat. And habitats matter because they create biological selection. They determine who can live there, what metabolisms are favoured, and how energy and matter move through the bottom ecosystem. That is where the holes begin to matter to biogeochemistry in a more serious way. Lake Huron sinkhole research has shown that microbial communities in low oxygen, sulfur-rich settings can cycle sulfur and carbon in ways unusual for ordinary Great Lakes waters. The 2006 exploration of a submerged sinkhole ecosystem in Lake Huron reported evidence for chemosynthesis in dark incubations, and described how these systems support microbial communities adapted to chemically unusual groundwater. Later work and NOAA summaries have linked those sinkholes to layered microbial mats, sulfur cycling, methane production in sediments, and strong contrasts between venting groundwater and surrounding lake water. If the Lake Michigan craters are connected to groundwater seepage, bedrock dissolution, or other subsurface exchange, they could offer another site where scientists study how groundwater shapes sediment chemistry, how biogeochemical gradients form at the lakebed, and how microbial life responds to persistent chemical disequilibrium. That is a meaningful scientific payoff, because such systems are rare enough to be useful natural laboratories. The holes may also matter because they could help scientists separate relic features from active ones. Some underwater depressions are ancient forms that no longer do much beyond sitting there as inherited structure. Others remain chemically or hydrologically active, channeling groundwater, trapping dense bottom water, or venting gas. One of the main scientific tasks in Lake Michigan will be to figure out where on that spectrum these craters fall. Live Science reported that the recent survey did not observe obvious water escaping from the holes that would clearly indicate active groundwater circulation at that time, though Steve Ruberg said he still expects circulation will eventually be detected. That kind of uncertainty is scientifically productive. It tells researchers exactly what they need next: repeat visits, chemistry sampling, seep detection, and perhaps seasonal comparisons. If the holes are active, they could reveal a living process. If they are relics, they still reveal a past process and the basin conditions that allowed it. Either outcome is useful, but each speaks to a different kind of science. Then there is the early Earth angle, which sounds at first like the kind of phrase that would get exaggerated very quickly, but in this case it rests on real, prior work. NOAA, Sanctuary Material and Microbial Sinkhole Research from Lake Huron, have repeatedly described those better studied sinkholes as analogues or time capsules for conditions on early Earth, especially because they combine low oxygen, sulfur-rich chemistry and microbial communities that use sulfur-based energy pathways uncommon in most modern surface habitats. Those comparisons have gone beyond storytelling. Researchers have used Lake Huron mats to study how microbial communities migrate through the day, how oxygen production interacts with sulfur-oxidizing bacteria, and how similar systems may have influenced Earth's long oxygenation history. If Lake Michigan's craters turn out to host comparable chemistry, they could provide a second Great Lakes setting for studying the same broad questions under somewhat different depth and habitat conditions. That would make them relevant not only to freshwater ecology, but to planetary history. That may sound like a large leap, but it is the kind of leap science makes carefully when multiple pieces line up. First, there is the geology, which may permit groundwater movement through carbonate rock. Then there is the possibility of chemically distinct bottom water. Then there is the chance for microbial communities that draw energy from sulfur compounds or other chemical sources, rather than from the usual oxygen-rich surface world pathways. Once those steps are in place, the early Earth comparison stops sounding fanciful and starts sounding methodological. Scientists are not saying the lake has turned into a literal ancient ocean. They are saying that some modern environments preserve chemical and biological interactions that help us understand ancient ones. The holes matter because they may point towards such an environment in a place where researchers can revisit, sample, image, and compare over time. That is an excellent scientific situation to have. The scientific meaning also extends into resource management and conservation. Wisconsin shipwreck. Coast National Marine Sanctuary was not created only to protect old wrecks as museum pieces. NOAA's Sanctuary Information and associated coastal science work make clear that management in the area also involves habitats, water quality, invasive species, and understanding how natural and cultural resources interact. A newly identified crater field adds another type of resource to that picture. It may need to be monitored not only because it is scientifically interesting, but because it could host fragile biological communities, reveal active groundwater discharge, or affect how the sanctuary understands its own benthic landscape. In protected waters, mapping is not just about curiosity. It supports decisions about where to place moorings, how to avoid damaging sensitive areas, how to interpret the sanctuary for the public, and how to plan future research efficiently. The holes therefore matter not only as scientific objects, but as management-relevant features in a nationally protected part of the lake. There are practical broader uses too. Great Lakes mapping advocates and NOAA-linked planning documents emphasise that better bottom maps support safe navigation, fisheries science, infrastructure awareness, storm and flooding models, and habitat protection. A Pease reporting on the Lakebed 2030 effort noted that high-resolution maps help identify underwater outcroppings and ledges where fish congregate, improve population estimates, reveal shipwrecks and infrastructure, and strengthen models of storm surge and flooding. NOAA's Great Lakes Spatial Priorities work says mapping data are essential for safe navigation, sustainable fisheries, habitat protection, and decision-making. In that context, the Lake Michigan craters are a vivid example of the kind of feature course maps can miss, and modern multi-beam work can recover. One discovery can therefore become evidence in a much larger policy argument. Detailed Great Lakes mapping is not a luxury. It changes what scientists and managers know is actually down there. They also matter because they link scientific communities that do not always meet in the same place. The discovery happened in a sanctuary known for maritime archaeology. The explanation may lie in geology or hydrology. The most exciting long-term implications may fall to microbiology and biogeochemistry. The mapping itself belongs to hydrography and remote sensing. That kind of crossover is where many of the best field discoveries gain strength. An archaeologist may notice a pattern because they are already surveying a wreck-rich zone. A geologist may recognise the carbonate context. A microbial ecologist may realise the chemistry could resemble a known sinkhole system. A hydrologist may ask whether groundwater is entering the craters. A manager may ask how this changes the sanctuary map. Science advances quickly when one patch of lake floor forces several specialties to look at the same coordinates from different angles. The holes may therefore matter partly because they create a shared problem that no single discipline can solve alone. Another scientific payoff lies in simple comparison. Lake Huron already has its well-studied sinkholes. If Lake Michigan's craters prove similar in origin or chemistry, researchers could compare two Great Lakes systems shaped by related regional geology, but differing in local depth, basin history, sediment cover, and perhaps biological response. Comparative science like that is powerful because it reduces the chance that one remarkable site gets treated as a one-off curiosity. Instead, scientists can ask which features are general to Great Lakes submerged sinkholes or craters, which depend on basin-specific conditions, and which chemical or ecological signals reliably indicate active groundwater influence. If the Lake Michigan holes turn out to be different in crucial ways, that would be valuable too. It would expand the catalogue of submerged Great Lakes landforms, rather than merely duplicating Lake Huron. Either way, the scientific meaning grows through comparison, not just through isolated description. There is also a humbler meaning, though it may be the most important one in the long run. The holes are a reminder that even in heavily used, economically central, culturally familiar waters, major features can sit unnoticed until the right tools arrive. NOAA's Great Lakes mapping material, the Lakebed 2030 effort, and national mapping reports all reinforce the same point. The Great Lakes remain undermapped relative to their importance. That is not merely a gap in convenience, it is a gap in understanding. Features like the Lake Michigan craters can affect geology, habitat interpretation, and perhaps chemical exchange. And yet they were not part of the public or even general scientific picture until recent survey work. That means the basin almost certainly still contains other surprises, whether geological, archaeological, ecological, or infrastructural. The scientific meaning of the holes is therefore also epistemic, if we want to use a slightly formal word. They show us something about what we do not yet know, and that in a way is the most useful thing a discovery can do. It can reveal a specific feature, yes, but it can also recalibrate the limits of confidence. Before the circles were mapped, the bottom in that part of the sanctuary may have seemed broadly understood enough for the purposes at hand. Afterward, the same area looks less complete, more structured, and more open to questions. Science benefits from that kind of correction. It stops researchers from assuming the flaw is simple, where it has only been poorly resolved. It encourages better instrumentation, more careful follow-up, and a little more humility in places that seem ordinary from shore. The holes may mean for science that Lake Michigan is geologically livelier, chemically more varied, and biologically more interesting than many people assumed. They may also mean that the Great Lakes, as a whole, deserve to be studied with the same seriousness often reserved for more obviously exotic environments. So the real importance of the mysterious holes is not that they make Lake Michigan spooky, though they certainly help with that. It is that they sit at the intersection of several scientific questions that are all worth asking anyway. How does groundwater move beneath Great Lakes basins? How do carbonate rocks and glacial deposits interact below a modern lake floor? How do isolated chemical environments shape microbial life? How much high-resolution mapping is still needed before the Great Lakes are genuinely understood? What can rare modern habitats teach us about much older Earth systems? A single crater field may not answer all of those questions on its own, and it may never need to. It only needs to be real, measurable, and strange enough to point science in productive directions. These holes already seem to have managed that, and as more surveys, samples, and comparisons build up around them, they may turn out to be one of those discoveries that begins with a curiosity on a map and ends by quietly changing how an entire freshwater world is studied.